compound events in the tropical South Atlantic. This research obviously is the result of a collaborative work. I would like to thank Thomas Froelich, Noel Kinsey, Alistair Hobday, and Frederick Berger. Compound events are defined as a combining of multiple drivers and all hazards that contributes to societal and environmental risk. As such, they can overwhelm the capacity of both natural and human systems to cope. So, causing socio-economic impacts such as loss of essential ecosystem services and income. We've seen so many talks about that. For this reason, it's imperative that we understand the physical processes by which weather-related and climate-related hazards combine in order to improve their predictability, assessment of their impacts and risks, while developing methods of detection and attribution. And, so our knowledge of compound extremes is more on land, as always. So there are different types of compound events. And this is a good paper that explains this typology and everything. So here I show a few types. They can be multiple hazards occurring at the same time, such as the event of a drought, the top left panel, together with occurring with a heat wave in the bottom left panel in the summer of 2022 in Europe, leading to widespread stress of vegetation and lowering expected yields of both winter and summer crops in Germany, Hungary, Italy, Poland, Romania, Slovakia, Spain, and Ukraine. So big effect there. So they can be previous climate conditions or weather events increasing a system vulnerability to a successive event, such as the drought and the heat wave, leading to a high risk of a flood. So if you have obviously a dry condition, it's more likely you're going to have a success floods, and that's what happened in Germany in 2021 with devastating consequence. So, and they can be spatial concurrent hazard leading to regional or globally compound effects. Then the compound is in effects, such as ENSO. For instance, ENSO can lead to droughts, heat waves, and floods everywhere globally, affecting several breadbasket regions at the same time. So our knowledge is more advanced, as I said, for extreme and compound events over land. In the oceans, extreme events of warming, called marine heat waves, you're all familiar with, have received a lot of attention recently. But marine heat waves, as you know, can cause devastating impacts on marine life. They have different physical mechanisms and drivers. But we found that in many cases, they can co-occur with extreme events on land, such as drought and heat waves on land. But they can also co-occur with other extremes in the ocean, such as extreme of acidification or acidity and deoxygenation. This is a work that I've developed a few years ago, and is an example of a compound event of drought in the left panel here. The negative precipitation in brown, that occur in eastern South America. And this occurred simultaneously with high temperatures over land and high temperatures too over the West and South Atlantic. In this event, in the summer, austral summer of 2013-14, an atmospheric blocking represented by these persistent winds here, uncyclone circulation, these vectors here in the left panel, or the right panel, was established over Southeast Brazil, and preventing the development of the South Atlantic Convergence Zone, which it brings the rain and clouds for this region here. This is the South Atlantic Convergence Zone. So the blocking didn't allow the development of the convergence zone, and so we had a lack of clouds, rainfall, and leading to the droughts. So, and the decrease in cloud cover also increased shortwave radiation into the ocean surface, and weaker winds decrease evaporative cooling, leading to then the marine heat wave. This is the effects, and this process obviously happened to overland, and that's why we had the heat waves overland as well. So we then applied the methodology by Hobday et al. 2016 to identify all marine heat wave events during austral summer for the period from 1982 to 2016, and we found that up to 6% of all marine heat wave days occur simultaneously with atmospheric blocking for this region and drought. The composite of SST anomaly for all the events is shown in the left here, and the mean signature of the SST warming is similar to that one that I showed just for the event of 2013-14, and the anomalous anticyclonic circulation, a hallmark of atmospheric blocking, is also evident during these events, represented by the vectors in the left panel. So the time series of anomalous blocking days per summer is strongly correlated to SST anomalies for the same area of the Western South Atlantic that you can see in this right panel here. And we have actually correlations up to 0.8. This corroborates our hypothesis that as for the 2013-14 marine heat wave, atmospheric blocking over subtropical South Atlantic is linked to ocean warming and extreme temperatures over land. So in the same study, we also made various analyses, which I'm not going to show here, to find the remote drivers. And these blockings are remotely forced. And the complete picture that emerges is showing this schematic. So tropical deep convection in the Eastern Indian Ocean, generally associate with Madden-Julian oscillation, trigger Rossby waves, trains, that ultimately lead to atmospheric blocking of the Western South Atlantic, and leading to then the drought and both land and marine heat wave. So my first point, the consideration is that, for instance, we have more advanced knowledge and better season forecast for precipitation. So if we know that these events of marine heat wave, for instance, are compound with droughts, so we could actually tap into this information already that is available for land and advance much quicker our knowledge if we have in mind that they occur simultaneously, most of the times at least. So we also noticed that these events are associated with a reduction of primary productivity. This is shown here in a box by this blue kind of negative values. And the event of 2013-14 is associated with a minimum of chlorophyll concentration. You can see this in a PDF for the whole period that we have satellite data, and here too as a minimum of a chlorophyll for this region here. Where the core of the marine heat wave happened. So we also have identified another effects. For instance, this event was associated with a reduction also in decline of the production of this species of clam, which is very important where I live, 27 South. And this region is also the biggest producer of oyster, supplying 90% of the market in Brazil and export too. They are cultivating shallow waters along base between the island and the mainland, and are greatly affected by extreme temperature. As you probably know better than I, under extreme temperature, oysters do not reach commercial size, and the extreme temperatures can also lead to the development of pathogenic microorganisms, increasing the risk of infection when consumed by humans. So I like to show this diagram to summarize the effects of this compound extreme. That is just for the event of 2013-14 that involved drought, heat wave, and marine heat wave. And it led to water and power shortage in Southeast Brazil, a region that is heavily populated, home to more than 80 million people, and responsible for 60% of the Brazilian gross domestic product. It reduced Brazilian soy, coffee, and sugarcane production, impacting food supplies globally, increasing worldwide prices. I get calls sometimes from the city and the stock markets about this event because it really spiked the prices of these commodities. It decreased the production of oysters and the catch of some commercially important fish species while decimating clams along the southern coast of Brazil, as I just showed. This event affected human health by increasing the risks of a heat stroke and vector-borne disease. It tripled the cases of death by dengue fever in the São Paulo region. In addition, compound events like this have a disaster impact on ecosystem degradation and loss of land and marine biodiversity. So my second point is that looking at this problem as a compound, we can see the risks in several sectors, industries, and I think we should work together with our colleagues, and we would have a better chance of convincing our policymakers that this actually have a big impact on the economy, particularly if they're going to become more frequent. So. We also investigate the most extreme marine heat waves globally, and this study was led by Alex Zenkupta from the University of New South Wales in Australia, and it shows, among other things, that a large proportion of the most extreme marine heat waves in the extratropical regions were associated with large, persistent, high-pressure systems, similar to what I just showed for the South Atlantic. So this is not just what I show this compound between drought and marine heat wave is not exclusive of South Atlantic. And we noticed that they were also in this study associated with low levels of nutrients and chlorophyll. So our most recent work, however, focuses on triple compound events of marine heat waves, low productivity, and high acidity in the tropical South Atlantic. So now I'm going to gear a little bit for compound events in the ocean. But first, we analyzed the spatial patterns and temporal evolution of the marine heat waves in the tropical and South Atlantic. Here, I show the trends of a marine heat wave cumulative intensity for the period from 1982 to 2020. And we can see that during austral summer, where the temperatures are already high in the maximum, the stronger positive, we have a strong positive anomalies, cumulative, marine cumulative anomalies, surpassing even 20 degrees Celsius per decade. And they tend to occur more in the western side. They are stronger, the positive trends in the western side of the basin, but also particularly in the western South Atlantic, where I just showed the previous study, but also in the equatorial region and in the Brazil-Malvinas confluence region. But they are also, positive, particularly in the eastern equatorial Atlantic, the Angola front region, which is very important, fisheries here, and also in Agalhas leakage region. So the consequences of more powerful marine heat waves can be amplified by the combination with other extreme events. We then analyze the extreme events individually of individually of ocean warming in here marine heat waves, if you wish, left, low chlorophyll, extreme events in the mid panels and high acidity extremes in the right panels for the period, unfortunately, from the period from 1999 to 2018, because that's when we 3 data sets overlap. The top panels show then for the first decade and the bottom panel for the second decade of this period. And you can see a widespread increasing, particularly in these high acidity events. And here is the difference between the 2 decades, just to highlight then it's easy to see where we have actually a real increase in marine heat waves. Low chlorophyll is more within the gyre, but the high acidity events were all widespread increase in the South Atlantic and tropical Atlantic. So, but now what we analyze is the number of times when they occurred simultaneously. So what you're seeing now here is the triple compound events of marine heat wave, low chlorophyll, and high acidity in these left panels. And in the middle panels, you can see the double compounds, just marine heat wave and low chlorophyll, and in the right panels is marine heat wave and high acidity. And so again, the top panels is for the first decade and the second panel for the second decade. And we can see that particularly related to high acidity, there was being not much triple compound in the first decade, but you can see that that's a lot of those happening now in the last decade. And so but here is marine heat waves with low chlorophyll, and here just marine heat waves and high acidity events. So the recent increase in occurrence, and the thing is that we noticed that particularly they have occurred practically every year since 2014, this triple compound event, which puts us in check the capability of a marine ecosystem to recover from these compound extremes. So this is more obvious is in the time series. So this recent increase, then an occurrence of these triple compounds can be seen here. This is the time series of normalized monthly intensity of marine heat waves in red. The legend is here, but extreme events of a low chlorophyll, blue, and high acidity in gold. Average over these boxes here, Western Equatorial Atlantic, Western Subtropical Atlantic, and the Brazil-Malvinas confluence region. And we can see that there is an increase, particularly in acidity, high acidity episodes after more or less 2014. And this is the case too for the western side of the eastern side of the basin, for the equatorial region, the Angola front, and this region here, which we call the Agulhas leakage region. So we then select the reason why we selected these areas for obviously several reasons. They are very, some of them are highly productive, biologically productive, but they are also where the most significant trends of marine heat wave cumulative intensity occurred during the last 4 decades. They have more incidence of triple compound events, and they encompass most of the potential mechanisms that can lead to compound extreme of ocean warming, high acidity and low oxygen, according to the work from Guibourd et al. 2021. We are not doing the oxygen here, but because they are areas of high variability. So this is figure 3 from Guibourd's and colleagues' work, and exemplify the process at play. And we already analyzed, I don't have the time to show, but this, and we identified that in the western equatorial and subtropical Atlantic regions, we have the compounds are caused by air-sea interaction, which is this mechanism here in the panel A. So in Angola front and Brazil-Malvinas confluence, we identified that these shifts on the front leads to this compound extreme, this is the panel B there. And Angola also can be caused, the triple compound, by shifts on by upwelling and in the equatorial, in the equatorial region too, we can have in panel C, Eastern Equatorial, the process of upwelling. And eddy trapping in Agulhas leakage region is the main cause of the triple compound. So we also found that the triple compound events were widespread during El Niño events, mainly with the major El Niño event of 2015-16, and to less extent with the weak 2018-19 El Niño event. As an example, I show the spatial coverage of compound events in 2015-16 in the left panel here, and the average over all the years in the right panel, just for the Agulha leakage, just an example. And if you just focus on the inner triangle numbers here in the inner triangle, which means the coverage of a triple compounds, we see that during El Niño years, or this specific El Niño year, we had 52% of the Agulhas leakage area covered by triple compound against only 2 neutral years. And so this is not bad news. In fact, it's good news because we have a lot of skew in predicting marine heat waves, mainly due to ENSO. This is from the work of Jacox. We will give talking to us and colleagues soon. We will be hearing from him, and the map of the left indicator, he probably knows much better. I'm not going to go too much into it. Just to let you know that we have this -1 means no skew and 1 good skew, and you can see the hallmark of ENSO in predicting marine heat waves. So, and places that has impact marine heat wave, like the equatorial or tropical Atlantic, for instance, can be skillful predicted in advance. So it is important to know the causes of these compound extremes to see if we can do a good job on predicting, and this is important as a tool of early warning and be provided for resource managing and ocean stakeholders. So my final considerations then are that ocean warming combined with acidification can negatively affect many species survival, growth, and development, as well shifting in community structure. You know better than me, I'm a physical oceanographer, but some other studies have shown that this can be mitigated by increasing in food availability. However, our study shows that in the tropical and South Atlantic, double compound events, extremes of marine heat wave and high acidity often occur simultaneous with low chlorophyll concentrations, and therefore a decrease in food availability, probably. So then this mitigation probably is not available there. And another consideration that I would like just to do is that, and maybe guide some discussions in this session, is the question of how we define an extreme. And there's been a lot of a debate about this. And if we do only considering the hazard, the question is incomplete in my opinion, and it depends on the impact in the marine ecosystem or human system. And we needed to know the degree of vulnerability and exposure in response to the hazard. And in my opinion, this obviously requires transdisciplinary work, and then we can see how best we define these extremes. And my last then slide is just to give an idea that, let's say that the return period of these events, like this that happened in Germany in 2021, decrease. In other words, these events become more frequent and they are not considered any longer extreme. But the question is, are we prepared for the impacts of this? I mean, we might statistically not consider them anymore extreme, right? They become so common, but I don't think we are prepared, and there is still extreme in their impact on us. And I wrote this perspective with Ted Shepard of the University of University of Reading, and we discussed then we needed to change our way of thinking, particularly physical oceanographers, climate scientists, focus on the physical aspect only, and by doing so we are deriving reality from a conceptual framework instead of deriving a conceptual framework from reality. And I just finish here, and this is the people that work with me in my lab in Brazil. Thank you.
Thank you, Regina. Are there any questions out there? You don't have to come up to the mic, I'll bring it to you.
Thank you very much, Regina. My question was about changes in the frequency of these over time, and I'm curious if you see evidence for changes because of actual changes in the coupling between them, or is it just the trends in the single extremes driving the compound trends?
Yeah, I didn't have time to show, but for the Western South Atlantic, which I've done more focus my work, we had not only in historical last 40 years, we had an increase in marine heat wave frequency, intensity, duration, and extension. But then we analyzed in the CMIP6 models, and also obviously, that is, if I use it, particularly if it's a baseline, a constant baseline, a standard baseline, we have an increase, really great increase in the future. But we look at the mechanism too. So it's not just related to the warming, the global warming or the rise temperatures, which obviously it will put it the threshold. Easy to achieve the threshold, but we noticed that the blocking also increase in the future, which is the mechanisms in this case that leads to the marine heat wave. So I'm not sure if I answered your question properly. Yeah.
Thanks so much, Regina. That was great as our first talk. I'm curious if you can speak any further to whether you have seen changes in terms of the social responses to these events as they have become more frequent, particularly maybe in the clam fishery that you highlighted or oyster aquaculture. Have they taken any measures to sort of be more prepared for events like this?
That clam that I showed actually is the decrease started in 2014-16, but we have follow years with and in 2017 actually the local fishermen and couldn't find them, you know, and we have the aquaculture, but in Brazil is still very not developed this type of thing, you see, of having a forecast that can be delivered to who needs the end user, for instance. They know that high temperatures cause all that impact, particularly in oyster industry, but they don't have much, you know. So we need really to work on science to society aspect is really not that good at all. In Brazil, still, we have a long way to go, unfortunately.
Any other questions? I have one for you, sorry, because we have more time. I'm going to make you stand a bit longer. I was really interested in your talk. I thought it was really great to bring in these compound events. You know, the literature so far has really been focused on temperature extremes. Bringing in productivity, bringing in acidity, obviously two very key variables there. What do you think are the next variables we need to be considering?
I would like to have a look at oxygen, but we didn't have like a, you know, this data set available. And I think that we now in Clara has, we created a marine heat wave focus, research focus to get into it. And we see that we need to understand coastal, we do this analysis all with satellite data, sea surface temperature, and we needed to know in subsurface, which is really important for biology, right? We are just looking at them. Where we have data is really hard because we don't have long-term data in subsurface, but where we do with the Pirate array in the tropical Atlantic, we notice that there are some events that happen in subsurface that has no signature in the surface. So if we are using this assessment just using sea surface temperature, we are missing, and coastal marine heat waves or extremes we haven't done. For instance, in Brazil, we don't have long-term measurements of these variables in the coastal region to actually have a climatology and then define what is an extreme to, you know, do a better job. I'm not sure if I also
No, that's perfect. Okay, thanks, thanks, Regina. So our next talk is going to be online from Andrew Pershing, so hopefully we'll get a video on screen soon.
Hi, everybody. Andy Pershing here. I am so bummed out not to be able to join you in Norway, which is one of my all-time favorite places. But I am really excited to have a chance to talk to you about our work trying to do rapid attribution of ocean temperature. So trying to isolate the signal of climate change in daily observations of ocean temperature. So we all know that we live on a planet that's warming. That's the purpose of this meeting. That's why we're here. The challenge that we face, though, especially when we think about communicating with the public about climate, is that this is not what we experience. We experience actually daily changes in the weather, right? And so it's not that the climate change signal isn't apparent in our daily weather. It's that it's just really hard to pull it out of all of the noise of daily changes of the seasonal cycles that we experience. And this is also true for the animals that are living in the ocean. Climate Central has developed a new system, we call it the Climate Shift Index, that allows us to do this every day, everywhere for air temperature. So we can, for example, say that today in Bergen, that the very nice conditions that hopefully you're getting a chance to enjoy are 3 times more likely due to climate change. That's what the red color on the map indicates. And what I'm here to do is to talk about how we're trying to fill in the blue on the map. So one of the keys, though, that we had to answer before we could roll out the Climate Shift Index or before we can do this for the ocean is how do we measure this change? How do we isolate the strength of the climate change signal? So we do this by thinking about observers. We're taking a very human-centered approach to the attribution problem. So we're going to think about this guy, not fully human, but mostly human. He knows a lot about the world. But this guy, you know, he's not quite fully getting it. He assumes that the world is static. In contrast, there's another, you know, very similar person, very similar background view of the world, except he understands that global warming is happening and that it has an effect on temperatures. So we're going to call the guy on the left the counterfactual observer, and we're going to call the guy on the right our modern observer. So we're going to talk about how much they know about the world. We're going to encapsulate that knowledge through a probability density function. So here's the PDF for temperature. Blue represents our counterfactual observer. Red is our modern observer. And then we're going to ask for a particular temperature, so in this case, something that's out on the tail, how surprising is that temperature to the observer? And that's because in information theory, surprise is actually information. It's how much new information you're getting about the world from the event that you're observing. And this is formally minus log of the probability, or in this case, for our application, the probability density. So our modern observer, even though he knows a lot about climate change and his distribution is shifted, he is going to observe that event and say, that's unusual, right? It's surprising. And so we'll give him 2 bits of information, let's say, for that observation. Our counterfactual observer is going to say that's super unusual, and we're going to give him 4 bits, okay, right? Because he's going to learn more about the event. It's more surprising to him. Then the metric that we've developed, we call it the change in information due to perspective, or CHIP, is the difference between these two. So it's counterfactual minus the modern. And in this case, it gives us a score of 2. And what this means is this is the information advantage that our modern observer has through their knowledge that climate change is real. Okay, so how do we calculate the change in information? Well, for our applications in the air, we're using ERA 5, but for our ocean work, we're basing it first and foremost on NOAA's OISST product. We're going to analyze relative to a modern climate, which is determined by the global mean temperature. So for example, in 2020, we're going to use a global mean temperature of 1.2 degrees C, and this is change relative to a pre-industrial. And then we're going to have a counterfactual representing 0 degrees, representing no warming. And then we're going to use a multi-method approach to construct these probability density functions for both the modern and the counterfactual. We're going to do that using observed trends. So in this case, the trends out of OISST, and specifically how they're related to the global mean temperature. And then we're going to take climate models. So we're going to have the forced runs and the control runs from CMIP6 to generate another set of distributions. So this is a diagram from Daniel Guilford's paper. Daniel led the paper that is the basis of our method. So we have the climate model path on the right. You can see that that's actually going to generate 24 different PDFs that we will be able to apply our methods to. And then we have a pathway on the left that uses our observations. And the key here on the observation pathways, we're going to take the local temperature, what we've observed, say, for a month at that location, and relate it to the global mean temperature. We're going to capture this through the beta parameter, or essentially the slope of that regression. And that beta lets us take the modern distribution, which we can observe now, and then we can shift it based on the amount of warming that we've had back to construct that counterfactual. And so we're going to have a lot of different ways of constructing these two contrasting distributions. However, for this talk, I'm actually only going to present work on the using the left-hand pathway, using the observational pathway. We're still waiting for the climate model calculations to finish. So these results are going to be preliminary. So what I'm going to do is walk through several heat waves that hopefully will be familiar to some of you. So starting off of Australia, we had a major event in 2015, 2016. The peak of that event occurred in early in 2016. And the anomalies, right, the temperature anomalies relative to 1990 through 2020 were above average, hitting temperature anomalies of 2 degrees C above average, where average would be that dashed line. Okay, so what does this CHIP score look like? What does our CHIP metric look like? Well, it looks a lot like the anomaly, but with different numbers. And at its peak, we were reaching CHIP values of 10. And okay, so what does this CHIP value mean? Well, one of the ways of thinking about it is you can think about it, because of the way logs work, as it's essentially the ratio of the probability in the modern versus the counterfactual. So it's by a log scale. So 10 is actually 2 to the 10th. So that means that we're saying that this event is 1,000 times more likely due to climate change. So it really would be hard to imagine that event happening in a world that didn't have global warming. The other thing to point out, though, is that throughout this year, even when we had observations that were close to 0, right, which is a 1990 through 2020 climatology, that we were calculating CHIP scores that were at levels 2 or 3, right? Level 2 means 4 times more likely due to climate change. So first lesson is that the climate signals are really strong in the ocean. And to see that, I can contrast that with the scale that we developed for our air temperature work, which goes from basically minus 2.5 to positive 2.5, so a much restricted range. Moving on to the Gulf of Maine, right, my favorite place. So Kathy Mills and I have documented heat waves in 2012 and 2016. So you can see that the anomalies are very similar in both years. The anomalies are kind of hovering right around 1, but then with spikes up to higher values. So a spike in the spring in 2012, a spike in the in the fall in 2016. So the CHIP values are really interesting, though. So you notice that the CHIP scores are lower in the spring, and then they rise throughout the year, even though the anomalies are fairly steady. And even though the anomalies are higher in 2012, 2016 has a stronger climate change signal according to our CHIP metric. So lesson here is that CHIP is not anomaly. It's telling us something fundamentally different, right? Because it's combining not just the anomaly, but it's also including the variability at that location and in that season, and it's including the trend at that location and that season, and how strongly and confident we are that that trend is related to climate change. So we have more confidence that the warming in the Gulf of Maine is related to climate change in September and October than we do early in the year, although we have pretty high confidence throughout the year, and that's, of course, true for the ocean. One more quick example. Here's the Mediterranean Sea last year. So very low anomaly. So again, we're kind of bringing in this idea that CHIP is not anomaly, but look at the CHIP scores. So this said very, very high levels. We're up at 2 to the 12th, or we're up at level 12, which gets us a ratio of 2 to the 12th, or over 4,000 times more likely due to climate change. So again, here, very low variability in the Eastern Mediterranean, very strong trends give us this highly attributable signal for this event in 2022. So this is just kind of walking through what we can say about the temperatures themselves, but we'd like to be able to start to connect this work to impact. So I'm going to talk about one impact avenue, and that's to talk about hurricanes. So hurricanes are fueled by warm water in the ocean. So here's Hurricane Maria in 2017 that was devastating for the islands of Dominica and Puerto Rico, and then Hurricane Ian in 2022 that went through Cuba and did a lot of damage in southern Florida in the US. So obviously, you can see that in both of these cases, we're dealing with warm water, right? And water that is warmer than we would expect, so positive anomalies. And what I want to do is zoom in on a couple of time periods for each of these, which are periods where the hurricanes went through rapid intensification. So for Maria, it went from basically a tropical storm to Category 5 between that one-day period between those two dots. So Hurricane Maria, when it underwent that rapid intensification, was doing so in water that was hitting CHIP values of 8 to 15. So extraordinarily high confidence that those water temperatures were fueled by climate change, that climate change made those conditions much more likely. Hurricane Ian, the climate signal is a little less strong. We're down at 3 to 10. But again, remembering back to air temperature, this is telling us that climate change played a role in making the warm water that made these storms into the devastating hurricanes that they became. Now, there's a lot of work to do to actually go one step further and say that climate change made those storms more likely, or the strength of those storms more likely. But we think this daily attribution method gives us a pathway to do that. So we think we can go from daily temperature attribution to attributable impact. Okay, a few quick conclusions. Attribution, we like to think of it as an information problem. We're going to quantify this as the change in the information due to these two perspectives, the counterfactual and the modern. A few lessons from our preliminary ocean temperature work. We see really strong signals in the ocean. I don't think that's going to surprise anybody here. There aren't a lot of climate deniers in the oceanographic community. We think CHIP is interesting and that it's telling us something different that complements our view based on temperature alone. And we think that this daily attribution approach gives us an avenue to talk about impacts. So as we move forward, we're going to be implementing the full multi-method system, so trying to fill in the blue areas of our climate shift index map. And we're going to start to work on applications. And this is where we would love to have people to collaborate with. So for example, hurricanes, I told you our pathway on hurricanes. We're also to think that, we can do things like looking at some of the daily heat metrics around coral bleaching. And we can think about fisheries impacts as well, especially some of the seasonal changes in fisheries. And finally, we really would love to be able to go even beyond the biology to thinking about the economic impacts related to climate change. And we think this daily attribution gives us a pathway to do that. So again, very sorry I can't be with you, but I'd love to correspond with you. So please feel free to email me or reach out to me on the Whova app. So thanks a lot and enjoy the rest of the conference.
Okay, as Andy said, you can email him if you have any questions. And next up, we have Clara Azarian, who's going to speak to us.
So, hi everyone, I'm Clara Azarian. I'm a second-year PhD student working with Francesco De Video at L'Océan and Laurent Bob at LMD IPSL. And I'd like also to thank also the other collaborators on this work on marine heat waves and global warming impacts on winter water in the southern Indian Ocean. So, generally, my PhD work focuses on the southern Indian Ocean and trying to understand how climate change is going to translate regionally and how it could impact pelagic ecosystems. And why do we focus on this region? Because it's one of the regions of the world where we have observed an increase in ocean heat content over the last decades. So we expect important climate change signal in this region. And it's also a region where we have important and rich biodiversity among the largest population of megafauna in the world and also important fisheries. But in the region, the fishing pressure is not as strong as in other parts of the world, so we expect also climate change to be a major threat to this biodiversity. However, it's quite complicated to study climate change impacts on biodiversity, and especially because of the scales. Climate change is often studied for large-scale processes, while ecosystems, and especially in the open ocean, are mostly driven by finer-scale processes. For instance, there are many studies showing the link between mesoscale activity and eddies with favored foraging zones for top predators. However, especially in the open ocean, this link between scales is quite a scientific challenge. It's also a challenge that is important for conservation because the scales are also relevant for conservation and management, for protecting marine areas or fishery management, for instance. So this is really crucial. But it's also complex because pelagic ecosystems evolve in a 3D environment that may evolve at different pace. And we need also to take into account that dynamics can also impact in a 3D way. So I put this slide, but in this session, I think everyone is a bit aware of what marine heat waves are. I used the statistical definition commonly used and introduced by Opta et al. 2016 that you have here. But it's just to show that behind the statistical definition that in my region we use at the surface, there are many different physical processes that can be related and that can impact depth in different ways. Radiative heat flux or geostrophic advection may have different consequences on the region. And so what are the winter waters that are in the title of this study? Well, in the region, in the southern Indian Ocean, we have a system of fronts where we have that delineates different water masses, and especially the polar front, PF, which marks the distinction between the presence and absence of winter waters. So south of the polar front, we have winter waters, which are described here. You have depth, latitude, and the temperatures are in the colors. And you see here this cold subsurface water mass that can be detected using a minimum of temperature between 100 and 400 meters. And it's called winter water because it's the remnant water from the previous winter mixed layer, which is then capped by summer warmer water mixed layer during the summer. And it's also ecologically important because, as you see here, this water mass actually facilitates the prey access for top predators, so making, for instance, king penguins or elephant seals, making their foraging more efficient. But those top predators are also dependent on the distance to their breeding island, which is fixed. And so the position and the characteristics of this water mass are crucial for their population dynamic. And so that's the question, is that how can warming, through extreme events such as marine heat waves, but then on longer time scale with global warming, how can they impact this 3D physical feature that is important for ecology? So for that study, for the marine heat wave impacts, we use different data sets. We use Austere satellite observation, so SST, for the marine heat wave detection at the surface, altimetry, and then for the 3D analysis, we use in situ profiles by autonomous Argo floats and also MEOPSIDI datasets, so hydrographic profiles collected by elephant seals, and we have them since 2004, and also Mercator analysis product. And then for the longer timescales, we use 12 global climate models, so from CEMIC 6 models, and 3 shared socio-economic pathways, so these ones, but we mostly focus on global warming levels, that is trying to understand what will happen to the winter waters for 1.5 degree warming world or 2 degree warming world, for instance. And so what we do is that we do the detection of marine heat waves using SST at the surface, and then we're going to look the Argo profiles when where they're found in the marine heat wave, how the temperature normally penetrates. And what we found is that marine heat waves are actually, and that's not surprising maybe for most of you, but they are associated with deeper temperature anomalies. But they may reflect different situations, and so here what you have is the temperature and depth, and so in red you have the Argo profiles in the marine heat wave, in blue Argo profile outside marine heat wave, and black are the Mercator reference. So you can see this minimum in the reference, this minimum temperature that marks the presence of the winter water, and then you see on the left example that during the marine heat wave, we still have this minimum of temperature, but it's a bit warmer, and we have important anomaly at the surface. But then on the right, you see that the profile in the marine heat wave is completely shifted towards warmer water, and we no longer have the minimum of temperature, suggesting that there has been a replacement or an advection, and it's the presence of another water mass. And to further investigate these advective processes, we can use altimetry data, so we have geostrophic velocities, and we can look at the advection and where the water parcel come from. So here you have in this example, the colors represent the latitudinal displacement. So if it's in red, it means that over 15 days, the water parcel has shifted southward. And in green, you have the contours of the marine heat wave, and you see that it matches that the marine heat waves are actually water parcels that have moved southward. And that's what we found also over the region, with a positive correlation between the anomalous southward displacement of the water parcel and the occurrence of the marine heat wave. And so how does that impact winter waters? When we could look at the Mercator reanalysis, and what we found is that we have a decreased probability of presence of the winter waters during marine heat waves. That's what we find here for different longitudes. But then when we have a marine heat wave and we still have this minimum of temperature, we also find that when this minimum is warmer and deeper. It's also interesting to compare marine heat wave subsurface characteristics between what we find in the Argo floats, which is random sampling, and the data that we have with elephant seals, which can be biased by the biology. So these are metrics, I'm not going into the details, but they are similar to what has been introduced by El-Zahabi and Schaffer in 2019. And what we found is that the marine heat waves that are sampled by elephant seals tend to be shallower and less intense than with the Argo floats that are random, which tend to suggest that there could be a behavior of avoidance of those deeper and more intense marine heat waves, which is actually consistent with what we know of the ecology, that is that their foraging is less efficient in warmer water, so they may avoid these intense events. Now, if we go in the future and trying on decadal timescales with CEMIC 6 models, we can look at the position of the polar front, which is the northernmost extension of the winter waters. And so here what you have is the pre-industrial position of the polar front in red dashed line, and then the envelopes of the intermodal variability. And then the position of the polar front for different global warming worlds. So global warming level, a world at 1.5 degree warming, 2 degree warming, etc. And what you see is that there is a southward shift of the polar front with global warming, but it's asymmetric between the west and the east of the Kerguelen Plateau. And especially at the east, we see that it's a nonlinear behavior with warming, and we can estimate a threshold at 3 degree warming where the polar fronts start to shift. And so to summarize, we have this physical feature, 3D feature, that is important for the biology, which can be impacted at different timescales for marine heat waves or global warming. And the mechanisms may be different depending on the timescales, but then the impact can be similar. In particular, we can learn from the impacts of marine heat waves. With the example of the 1997 event, where there was a big marine heat wave event that was associated with an important shift of the polar front and an important decrease of the breeding population of king penguins from Crozet because their foraging zone was shifted too much south. And so what we see is that this is an impact of a marine heat wave, but in our projections we see that this polar front may shift southward more permanently, and so this could mean the dramatic consequences for this population. However, for the Kerguelen population, since the polar front is more stable, up to a certain threshold, they could be less sensitive. So this study raises lots of questions that can be further investigated, and but what I'm focusing on more now is trying to understand whether the southward shift of the polar front that we observe could actually modify the circulation over the Kerguelen Plateau that you see here, and which is important for the larval connectivity and other ecological processes. And it's just to show that we could still try to learn from extreme events and impacts to then anticipate future impacts later, but trying to understand the dynamics also of climate change. So the main message and conclusions is that we're trying to understand more climate change impacts in terms of mechanism and trying to use extreme events as snapshots into the future and the future warmer climate, and that can be useful to anticipate what could be the potential future impacts. And with this example, we see that we can also include this 3D component and 3D environment, identifying some impacts on different timescales with major implications for top predators, but also that this spatial understanding locally of how changes can be and how asymmetric they can be associated with the known vulnerability of the species can be also really interesting information for conservation, for instance. And that's all for me.
Any questions out there?
Thank you. Very interesting talk. Close to my heart because I worked on elephant seals long ago. Is there any evidence with that shift of a shift in breeding of the seals, because they have to travel from Kerguelen to Heard Island, which is much further south?
In terms of breeding, I'm not sure, because I'm not an ecologist and expert on elephant seal, so I'm not sure there has been example of the shift, but maybe. I know that there is a paper, Mesretal 2020, who shows a shift in the diets using isotopes, and so maybe there's something to look at in terms of the breeding and foraging zones. But what they show in the paper is that the elephant seals, for instance, the female, do not tend to go breed more southward, but maybe the composition of the ecosystems, it may be changing as well. So yeah, that's all I can say.
Any more questions? I have a quick one for you.
Yeah.
You focused a lot on the kind of eroding of the winter waters with marine heat waves. Have you looked at what's happening in summer as well?
Oh, so the winter waters are actually also, they are present in the summer. So the term winter water is just to characterize the fact that they are formed by the previous winter mixed layer. But so it can be detected also in summer. So the study I've done is including both winter and summer seasons. So yeah.
Okay, thank you, Clara.
Thank you.
Next we have Mike Jacox.
All right, thanks very much, Steph. And yeah, I'm going to present, I think, the American counterpart to Jason's talk. I'll start with some discussion of global marine heat wave forecasts and then zoom in a little bit on the California current and sort of ocean variability more generally, not just marine heat waves. So I think a key point that may be obvious but is worth stating is that though marine heat wave, the sort of intense interest in marine heat wave and the term marine heat wave have really sort of boomed in the last decade, that marine heat waves themselves are not new, and they are a part of the temperature distribution, right? And there's a ton of tools and research on temperature. And so we can sort of stand on the shoulders of giants. We don't have to reinvent the wheel when we're talking about marine heat waves. And so in forecasting marine heat waves, this is true as well. So here I'm showing output from 6 models that contribute to the North American Multi-Model Ensemble, which is a collection of seasonal forecasts produced by North American modeling centers. These are the current forecasts, so put out this month, of global sea surface temperature anomalies, I think 7 months from now, so in November. And you can see the reds are warm anomalies. It looks like we're headed into an El Nino event. But the point is that these are available, and they're available starting in like 1980, and we can use them to create marine heat wave forecasts. So that's what we've done. Basically just, taking each of these models individually, looking at their own climatologies, calculating SST anomalies, determining thresholds for marine heat waves, and then you can take from each of these forecasts, you can classify every individual forecast as heat wave, yes or no, at any given time, right? And so every month you get a forecast extending out 12 months with about 70 ensemble members of marine heat waves. And we can evaluate this over the last 30 years using observations. We're using OISST. And so using this method, we have developed these global marine heat wave forecasts, which are publicly available at the URL here. They've been online now for about a year, and every month they're being updated. When the latest global climate models get run, we run our algorithm on it to calculate marine heat wave forecasts. And so you can go explore these. You can click on any one of these dots to look at the forecast in that region. You can go back in time and look at what the forecasts were like, and you can look at them with trends included or without. So we certainly hope this is useful, and please go explore and be patient with the website. It loads a lot of data on the fly. But I think thinking as a user, so first question is, how good are these forecasts? And here is a skill assessment using those 30 years, which Regina touched on earlier. This skill metric is called the Symmetrical Extremal Dependence Index. You don't need to know anything more than it's well suited to evaluating forecasts of extremes, and that 0 is basically no better than random and 1 is perfect. Anything inside the black lines is statistically significantly above 0. And so over large swaths of the ocean, we get these skillful forecasts, certainly at lead months or lead times of a couple months, and even out to 6 months or up to a year in certain parts of the ocean. But I think telling someone that your region has a SETI of 0.7 is probably completely useless information. So in trying to take a step of thinking of how that skill might translate to decision making, one way to look at that is to think of a threshold at which you might make a decision and what that means for the likelihood of being right or wrong. So if you get your weather forecast and it says 30% chance of rain, you can decide whether that means you're going to carry an umbrella, right? And maybe some of you will and some of you won't, depending on your own thresholds. And so the same thing is true here. You're basically trading off two ways that you can be wrong, right? So one way you can be wrong is this type 2 error where you can say there's going to be a marine heat wave, and ultimately there isn't. The other way is that you predict that there won't be a marine heat wave, and there is one. And so you trade those off, and in the weather analogy, it's one is the risk of carrying an umbrella and not needing it, and the other is the risk of not carrying an umbrella and getting wet because it does rain. And depending on your own sort of risk profile, you can decide at what threshold you might make a decision. So in the case of marine heat waves, this is, depending on your framing, low risk tolerance might be a low probability threshold. Like where even if the likelihood of a heat wave is elevated a little bit, I'm going to take action because I really don't want there to be a heat wave and I didn't act. Or it may be the opposite, where you really don't want to take unnecessary action. So maybe it's a closure of a fishery or something like that, and you really don't want to cause adverse economic impact unnecessarily. And so you're saying, I'm not going to close this thing until I'm really sure that there's going to be impacts. So that's one way to kind of dive into a specific location, I think, and parse out, like, what does it mean to make decisions based on these? But there's also, of course, a lot of interest in zooming in terms of the resolution and saying, you know, these coarse models, maybe they're not going to be useful for me to make decisions on a local scale. And so for that, we can turn to, or one thing we can turn to is downscaling, right? And so if anyone saw Sam Sidlecki's talk earlier in the week, you saw a really nice example of this in the Pacific Northwest. But the basic idea is simply that we take those same global climate forecasts, we use them as boundary conditions to run a regional model at much higher resolution. And in our case, what we've done is sort of a retrospective test of this method for the California current system, this 10-kilometer resolution domain that basically spans the US West Coast and out to 1,000 kilometers offshore. And we've run these retrospective forecasts for 30 years in the past so that we can test the skill of them. An important thing to note is while we had 70 some odd members in the global ensemble, here we've downscaled 3. Downscaling is really expensive to do. It takes up a lot of storage, so we're much more limited in terms of the size of the ensemble we have to work with. And so here's just an example of what these forecasts look like. These time series are for sort of a coastal band, extend, you know, the 75 kilometers next to the shore along the US West Coast. And so on the top is the actual forecast in green, the median, or the mean, sorry, and the dark line, and then the shading showing the spread of the ensemble. So obviously it's getting the seasonal cycle well, but more interesting is the anomalies, which are on the bottom. So this is showing one forecast initialized every year and extending out a year, and compared against the observations in black. So again, looking over 30 years, we can look at the skill. This is not for heat waves specifically, but it's for SST in general. And you can see that skill that is significantly above 0 out to 6 months or more, at least in this region, using the downscaled forecasts. But another benefit, of course, of having this high-resolution regional information is now let's move beyond just surface temperature, right? There's a lot more influencing the ecosystem. And so we've looked at a suite of different variables that have been found to be ecologically important in the region. So here I'm showing similar assessments of skill for bottom temperature, sea surface height, and buoyancy frequency in the upper part of the water column. All of them show considerable skill months in advance. This is not to say that everything is predictable, and this is the cherry-picked, really nicely predictable things. The counter to that is here, also things we would like to be able to predict because they've been used in ecological models in the region. So things like mixed layer depth, ocean currents, surface winds, and in all of these cases, the predictability is much less. So you're at maybe a month or two of forecast skill, if that, and things that tend to be subject, that either are the winds or that are subject to the winds, to the sort of rapid changes in the winds that are much less predictable than some of the ocean dynamics. All right, so we've got this physical forecast skill assessment, and the reason that we've done this is to inform ecological modeling and sort of hopefully some kind of ecosystem management. And there's a lot of different potential applications. So these papers represent a number, and the general idea is that they've been developed based on historical or near real-time conditions for some application, and so potentially they could be moved into forecast mode given the environmental conditions in the forecasts. And so I'll go to the next slide here to sort of summarize some of those applications. Some of them are about human-wildlife interactions, some might be about trying to understand fluctuations in stocks, or in distributions. And this is certainly not a comprehensive list. And these are potential ones. There are some already that have been implemented. And again, Sam's talk had some nice example of those. But the point I want to make here is that we can look at each of these forecasts and we can sort of summarize their needs. What region are they in? So south is Southern California, central is central northern California, and north is Oregon, Washington. What variables underlie the ecological models in that application? and then what months are the forecasts needed for. And so the argument I want to make here is that before diving into running all the ecological models and doing skill assessments if we can take the physical forecast skill assessments along with this sort of summary and just kind of line them up to look at the potential. And so if you look at any of these ones and you sort of take the region, the variables, and the seasons that you're interested in, you can look at the physical forecast skill associated with those times and places and variables and just see what is underlying that forecast. So here, the sort of the spread in skill across those regions, variables, and times is shown as these box and whisker plots. And you can see that for some variables, there's just like good skill across the board for everything you need to underline that forecast, especially ones that have few variables like SST and SSH that are quite predictable. And then some down here that are covering a large part of the year and that are using this full suite of variables that I mentioned. They have this huge spread in skill, right? So there may be variables, times underlying that model that are quite predictable, but others where the skill is very low. So the chances of success there might not be as clear. And so what I want to finish with is a promo for Steph Brody's talk. It's the last talk of the session today, and it, I think, builds beautifully upon this in two ways. One is that she actually has gone in and explicitly evaluated some of these ecological forecasts for the California current. And the other is this really important question, I think, that has not gotten enough attention about what is actually the added value of downscaling. Is the global model enough sometimes? And if you do downscale, is it always better? And what are the trade-offs between sort of large ensemble size and more limited downscaled forecasts? And thanks for listening.
Thanks, Mike. I appreciate the plug for my talk. Are there any questions? There's one behind you.
Hi, that was a great talk. I'm just curious, you don't have oxygen or hypoxic events or deoxygenation events listed in anything you've shown. Is there the chance to predict that? And have people been working on it?
Yeah, so I'll give I don't know if you're in the audience, Sam, I hope you are, because this is my third, I think, shout out to Sam Sidlecki's work in the Pacific Northwest. So they have been doing biogeochemistry in their seasonal forecasts. We have not yet, but this is something we're working on an LOI for proposal right now to add biogeochemistry to the seasonal forecasts. Yes, hugely important, and we haven't done it yet.
There's a question here first. I'll come back to you.
Hi, thanks for the nice talk. I'm not really working on this field, but when I see your figures, I see, like ENSO is coming out as the predictability, but I don't hear any discussion about the reasons why you're able to predict these marine heat waves. So is it just that you're predicting ENSO? So if you did sort of a relationship between skill in predicting ENSO, would you see that this is why you're getting skill in predicting the marine heat waves? And this maybe helps you address the second part of your question there about the downscaling. I mean, are you seeing added value from downscaling because you're picking up some sort of local processes beyond ENSO or something like this?
Yes. So yes, ENSO is absolutely the 800-pound gorilla. It's like there's persistence, which Jason showed. The ocean evolves slowly. You get skill from that. And then the big dynamical driver on top of that is ENSO. And absolutely, it jumps out in those skill plots. And in the paper, we get into this more explicitly, showing skill for different ENSO phases. And then the regional part, I think it both could be local processes, or it could just be better resolving the local expression of the broad scale, right? When you get the interaction of that broad scale forcing with local topography and things like that.
I'm not a modeler, but a user of the models. I was very attracted by your slide showing actually the prediction of heat waves. However, I'm interested in the Eastern Tropical Atlantic, and after 1.5 months, your skill showed that there is very little skill actually in this prediction. So what your advice would be for those model users? Just use your product, or maybe just apply your methodology to more regional models for the Atlantic?
So I guess yeah, like the east coast of the US is the same. The horizon for predictability is very short. So the two things I would say are, I think there are lots of applications on short time scales where a lead time of a couple weeks or even maybe days or a month could be useful. So if there are applications there, then something like this is useful. But absolutely the same methodology could be applied to sub-seasonal models, which are designed to really go out to say 60 days. Or to regional models. Yeah. But there are just inherent limits to predictability in the climate, and some regions are luckier than others in that respect.
Okay, I think we're out of time. Thanks so much, Mike.
Marine fisheries plays a critical elements of the socioeconomic support of the people living in Bangladesh. And small-scale fisheries are regarded, as one of the most vulnerable group of communities in the coastal areas of Bangladesh. So more than 17 million people earn their livelihood from the fisheries sector, and it contributes to 3.5% GDP of Bangladesh. So as I told that, Bangladesh is regarded as one of the most vulnerable countries to the face of climate change. And nearly every year, it faces different extreme climatic events, such as tropical cyclones, storm surge, floods, riverbank erosion. It affects the coastlines and its communities living in those areas. So under those altered climatic conditions, it remains unclear that how fishers make weather-related decisions, when to go out for sea, when to return. And so it's very important to understand how small-scale fishers respond and adapt to extreme climatic events. And it's very crucial for their sustainable livelihoods and their communities living in Bangladesh. So to sort that, we tried to identify the factors that contributes to the fishers' vulnerability to extreme events, and how the changes, socio-ecological changes, actually influence their vulnerability to extreme events. And most importantly, how the fishers make weather-related decisions when it's come to extreme events, when they are in the sea. Okay, so we conducted 100 surveys in 2 locations of Bangladesh, which contains both closed and open-ended questions. And you can see the locations over here. It pretty much distinct areas, but we try to cover. It has a homogeneous population, and most of the population over there are small-scale fishers. Okay, so to understand the vulnerabilities of their communities, we need to look for the socio-demographic profiles of those communities. You will see that 50% of the respondents just go to primary education. A small fraction actually goes for the secondary education, and 23% doesn't have any education at all. So, so the capacity to understand different climatic factors, climate change, they don't know actually what does it mean by climate change and what they do when it's come to climate change. 91% of the respondents are full-time fishermen. So which actually shows the vulnerability, because after the 12 months, all the 12 months are, the fishing season. At approx 4 to 5 months are fishing season, and rest of the months they remain idle or they don't do anything at all. 9% of the fishermen are seasonal fishermen. They only go, to reap the good harvest from the fishing season. The length of the fishing trip by the respondent, we'll see that previously it used to take 4 or 5 days in the deep sea. But right now it is taking 10 or 15 days, or within 10 or 15 days, sometimes they do not make enough harvest from the fishing trip. And most of the respondents' monthly income is 5 to 10,000 BDT taka. That means it is equivalent to 50 to 100 US dollar per month. It's not enough for them, and it's a small fraction, for people, for a community, or for a family which in average 4 to 6 members in a family. So it's pretty much difficult. So this is the vulnerable factors of the small-scale fishers currently in the coastal communities. So let's talk about the socio-ecological factors contributing to small-scale fisheries vulnerability. As you know, that due to low-lying delta association, Bangladesh is extremely, it's a breeding ground of different extreme climatic events. Storm surge, cyclones, nearly every year faces such extreme weather conditions. Seasonality and fluctuation of natural resources. Fishing is something, the natural thing. Fishers not always get the opportunity to get the full harvest. So seasonality is a weak factor which works as a vulnerability. Dependency on single species. Bangladesh's national fish, which is hilsa fish. So they are primarily dependent on catching hilsa fish. So that is the vulnerable factor, dependency on single species. Piracy and other unlawful activities is the most common thing facing the small-scale fishers. Landlessness and settlement areas exposed to coastal areas. Most of the fishermen live in areas where they are exposed to different coastal erosion or at the edge of the sea. Lack of access in political processes. Fishers' limited capacity to bargain. They do not have the capacity to participate, to bargain or to make the price of the fish. So they do not have that will. Lack of access to formal credit system because they do not have enough properties, and so that is why they cannot participate or they cannot get access to the formal banking channel. So they have to depend on NGOs or other microfinance organization which carries additional interest rates. Okay, so for the rest of the presentation, I will try to focus on their behaviors and their adaptation patterns. So we have seen that fish stocks have not decreased, but the number of fishermen has increased drastically. Fishermen, their children, their grandchildren are coming into this profession because of the lack of scope of alternative livelihood in those areas. So fish I cannot see in the markets in a very good number, but that the number of fishermen has increased drastically. The abundance of fish near the shore has decreased significantly due to the emergence of sandbars and islands, due to the huge transportation of silt to the Bay of Bengal. The Bangladesh is now experiencing different sandbars and islands in the Bay of Bengal. So the fish is not currently at the shore-centric, but they have moved to the deep sea. So the availability of fish increases during storm or heavy rain when the tidal wave is shore-centric. So this is one of the most important findings that we have found. When there is extreme situation, when there is early warning signals is forecasted, they still go to the sea because that is the situation when the fish is the most. So they actually risk their own life and go to the sea and return to the shore as the winners. But most of the fishers do not come as the winners. Sometimes they die in the sea. Sometimes they are stranded on the coast of India. As fishes are more available in the deep sea, their gears, fishing gears, has also changed. You see that they had to change their shine net. This is a traditional fishing net they used to do, which is 4 to 50 meters in length. But they had to change their fishing net to lomba net, which is 100 to 120 meters in length. They also responded that they have experienced increased frequency of cyclone. But we are also thinking that they have experiencing the increased intensity of cyclone, but not. They are currently experiencing the frequency of cyclone. The cyclones are getting frequent. So they only avoid going to the sea when the height of the wave is 9 feet. 3 to 6 feet is pretty much normal. They consider it very normal way. 3 to 6 feet height is also the situation when the weather forecasting organization tells that, okay, you stay at the shore, do not go for the fishing. But that is the ideal time. They think that it's time to go for the fishing and return with a good harvest. East-west wind direction prevents fishers going out to sea because it's pretty much, we have seen that from the field that east-west, when there is east-west wind directions, the weather situation is kind of extreme. And it pushes the fishermen to the edge of the Indian coast. And sometimes they cannot return. They can sometimes return. So it's very much difficult for the fishermen to come and return. So Yeah, so this is the situation right now. Most fishers avoid fishing at sea in response to local cautionary signals. So these are the types of weather signal that is currently available in Bangladesh, but they avoid going out to sea when there is a local cautionary signal is 3 to 4. Okay, so let's discuss about what they do when they have access to early warning signal. They have the early warning signal access when they are within 50 to 100 kilometers from the shore. So when they have the access to the early warning signal, they try to come ashore right away because of different situation, different initiatives taken by the government and the Coast Guard immediately tells you that go to the shore, and they try to come right ashore way in between 3 to 5 weather signal, and they use floating drum rings and empty drums. You can see that it is also attached with the fishing net, but they use that during extreme situations. And they try to move towards mangrove forest for safety. Bangladesh coastline, half of the Bangladesh coastline is surrounded by Sundarban mangrove forest, the largest mangrove forest in the world. They go inside the mangrove forest because the intensity of the extreme events got reduced when they are in the mangrove forest. And they change the location of fishing to storms, to somewhere without a storm. Because when there is extreme events, cyclones in the sea, there is no area they can go for a safe location. The only safe location is to come ashore at the sea. So these are one of the important quotations that I have attached here. You see that I can read it right now. So nowadays signals are given prior to every adversity in weather. Even sometimes signals are called out without any disaster. So that's why the sailors in this area still rely heavily on the traditional method of through experience. So based on the state of the sea, we can understand whether there will be storm or not when you see lightning strikes in the eastern sky. And we realize that the sky is getting worse. Besides, we see the red water at a certain place, locally called Rong Cholin. It's a locally Bengali term. And we assume that the sea may become extremely hostile, then there is the sign of shuri fish becoming impatient. So now more than signals, they more rely on the traditional method of identifying and deciding that whether they want to get back to the sea, get back to the shore, or remain in the sea. So let's talk about what they do when they do not have any early warning signal. They do not have any early signals. So they stop fishing activities immediately, and they try to return to the shore. And sometimes, most of the time, what they do, they drop the anchor in the sea till the storm cyclone passes away. So this is the most important thing that we have found. And they wear life jackets, and they lift the fishing nets on the boat immediately. And you see that they tie the knot together and make it like this and put it on 2 sides of the vessel. So what happened that in this situation, the direct effect of the waves cannot hit the boat directly. So it becomes, so they try to form a circular knot together with the fishing net, which is locally termed as heska, and leave it on the water. In this way, the high waves of the water do not hit the boat directly. And when there is an extreme situation, when they know that, okay, it is too late right now, they abandon the boats, the fishing nets, which is equivalent to $1,000 actually. So they abandon those properties in the sea and try to come to the shore. And which is another quotation for your reference. So if a sudden storm hits at the wild sea, there is no way to avoid it without anchoring. If we try to sail the boat, it will not be stranded on the shore, but will be forced to drift towards the east coast of India because of east-west wind directions. So instead of showing the courage to come to the shore, we rely on Allah during storm and keep ourselves united by wearing life jackets and knotting together the floating jerry cans. When the sea gets a little calm, they try to come to the nearby shore. So you see, as he said, that strong will, strong religious beliefs have been one of the most important components of resilience of the people living in the coastal areas of Bangladesh. So our present attempt to identify their behavior, their adaptation strategies may guide other communities as well to build the resilience of those fishing communities and protect them from the anthropogenic climate change impacts. Thank you so much. Yes.
All right, thank you so much. We are at time on that talk, so please, I hope that you can have conversations and folks can ask questions during the break. We do have a gap in talks. We have a talk canceled at 2:30, so there will be time for discussion then as well.
Okay,
Thank you. All right, our next speaker, Vianney Guibourd Luzinais. Sorry, I hope you will reintroduce yourself so that everyone will be able to pronounce your name properly.
Hi. Hello, everyone. So my name is Vianney Guibourd Luzinais. I am a PhD student, and I am going to present you part of my PhD work. And so for that work, I am working between l'Institut Agro in France and the University of British Columbia in Canada. And so the objective of my PhD is to work on marine to have ecological consequences. And for this PhD, I am supervised by Professor Didier Gasquel in France and by Professor William Chang in Canada. And in this presentation, I will talk about the large potential impacts of marine heatwaves on ecosystem functioning. So with the last 20 years, with the climate change, the frequency, intensity, and duration of marine heatwaves have increased. And some of them, as you can see it on the right panel, have resulted in biological and socio-economical impacts, leading to direct and indirect effect on the structure and the functioning of marine ecosystem, which in turn have jeopardized the ecosystem services provided by the ocean. If we look at spatial scale, we observe that marine heat waves occurred almost in all oceans, and on average, each year between 2015 and 2020, there were between 20% to 70% of marine heat waves days, which scale with the legend here. Oh, sorry, with the legend here. And in addition, we could see that the northern hemisphere appear more prone to marine heat waves compared to the south hemisphere. In this context, the aim of my study was to understand the expected effect of marine heat waves on the trophodynamics of various biomes. And so in this presentation, I will focus specifically on consumer biomass. So to assess this question, we used ecotroph marine ecosystem model to simulate different biomes. And this model represents marine food web functioning as a biomass flow along the food web, and leading to a continuous representation of the biomass distribution according to different trophic levels, creating at the end a biomass trophic spectrum. Associated to marine heat waves occurrences, the two parameters of the model, as the kinetic and the transfer efficiency, are perturbated. And furthermore, an additional loss in biomass transfer is expected in the case of marine heat waves occurrence. And this loss depends of the percentage of species undergoing a thermal stress associated to marine heat waves. So to take into account this additional loss associated to marine heat waves occurrence, we use species occurrence and sea surface temperature from different databases to identify each species thermal limit. And for the following, we declare a species undergoing a thermal stress when the thermal limit of each species fixed at the 95th percentile of the thermal niches of each species were exceeded by the sea surface temperature of each marine heat waves. And in a second step, we look at each marine heat wave characteristic according to the well-used and well-known definition of marine heat waves in 2016 and 2018. And we also match the sea surface temperature anomaly corresponding to each marine heat waves category in the ocean. And finally, we match these two data sets and being able to express the percentage of species undergoing a thermal stress regarding the marine waves categories. So, for example, here on the graph, we can see an almost continuous increases of the percentage of species undergoing a thermal stress regarding the marine wave categories. And so, as a first result, we express the percentage of species undergoing a thermal stress function of marine waves categories and historical ocean temperature all around the world, and for each historical ocean temperature of 1 degree Celsius thermal class. And we could observe that warm water species are more greatly affected by marine waves than species living in mild or cold water. And mainly because in warm water, species have narrow thermal niche, and are generally living near the upper range of it, which result in large reaction from a category 1 event. So when I am talking about warm species, I am around this type of thermal class values, and compared to cold water species corresponding to this temperature, where species have wider thermal niche and greater thermal safety margin, implying no reaction until a category 3 marine heat waves. And so in the following result I'm going to present you, we used the yellow, blue, and pink thick curve here on the graph to mimic the functioning of tropical, temperate, and polar biome, respectively. So here are the results from the ecotroph model we used, and well, the results are in preparation and will be soon submitted. And so we made a large range of marine heat wave simulation regarding the historical trend of marine heat waves based on the pre-analysis we made on NOAA data. And so here on the y-axis, we simulate marine heat waves up to 5 months and up to marine heat waves of category 4. And so basically, the color behind corresponds to specific characteristic of marine heat wave category and duration. And so in tropical biome simulation highlighted that biomass impact from a category 1 marine heat wave, which can reach up to 25% in the case of most extreme marine heat wave lasting 5 months and of a category 4. Here highlighted in the black circle. And if we look at the other indicator of biome response to marine heat waves occurrence, which correspond to the time to recover, and by time to recover, we mean the time needed for the ecosystem to recover 95% of the original biomass before the marine heat wave occurrence, it results in, for the tropical biome, in a fast recovery, which could be up to 12 months here on the black circle, associated to a marine heat wave of category 4 lasting 5 months. If we look now to, oh yes, sorry, I forgot, and which is more important about regarding what is more important compared to the figure I highlighted, is that in both indicators, so the biomass loss and the time to recover, both evolve almost vertically with marine heat waves characteristic, which highlight for the tropical biome a response mostly dependent of marine heat wave duration characteristic. If we look now at the polar biome simulation, no biomass impact are expected until a category 2 marine heat waves. And in the most extreme marine heat wave of category 2, similarly with the blacks highlighted by the black circle, it can be expect a decrease of biomass up to 15%. And if we look at the time to recover for the polar biome, we highlighted that it needs much more time than the tropical biome to recover, and it could be up to 30 months. 30 months to recover from a category 4 5-month duration marine heat wave, sorry, here. And so for this biome, compared to the tropical biome just before, both average biomass loss and time to recover respond almost horizontally comparing according to a marine heat wave simulation, highlighting that in polar biome, the response to marine heat waves occurrence is mostly dependent on marine heat wave category characteristic. And lastly, if we look at the temperate biome, in this biome, we see some impacts from marine heat wave of category 1, and in most extreme category marine heat waves of category 4 lasting 5 months, we can expect up to a decrease of biomass up to 23%. And compared to the tropical and polar biome, temperate biome has an intermediate recovery time, which could reach up to 20 months to recover from the most extreme marine heat wave simulation of 5 months, 5 months, and of a category 4. And if we look at the isoplate here of how the temperate biome responds to marine heat waves, we can see that this biome depend both on marine heat wave duration and category characteristic. Finally, in a last result, we showed that the food web compartment does not react the same way to a marine heat wave. And here on the figure, it corresponds to a simulation of a marine heat wave of category 3 and of 1.5 months duration, which is highlighted in the gray shade area. And this simulation are for the temperate biome. And so we have been able to follow the marine heat wave perturbation through time and through the food web. And so for low trophic level corresponding to trophic level between 2 and 3, we can observe an instantaneous large biomass decrease around 40%, but a pretty fast recovery after the event. Whereas if we look at mid-trophic level corresponding to a trophic level of 3 to 4, they undergo a lower biomass loss, around 30%, associated with a longer time to recover. And although high trophic level corresponding to trophic level between 4 and 5, they have an instantaneous low biomass loss, around 50%, they need about 10-fold time as low trophic level to recover. So to conclude, in this study, we highlighted that biomes I can't pronounce this one, instantaneously react to marine heat wave by a biomass decrease, and especially in tropical biome. Yet this impact may last for a longer or shorter period regarding the duration of the event. Secondly, we highlighted long time recover period associated to one marine heat wave occurrence, especially for the polar biome. And even if it was not specifically mentioned in this talk, on average, the time to recover for each biome is greater than the return time of marine heat wave in real life, as the data say that there is between 2 and 5 marine heat wave on average in each biome. And thus the consequences highlighted in this presentation could be amplified in real life. And thirdly, marine heat waves is disrupting the functioning and structure of food web with a stronger impact on higher trophic level, which are known to play a key role in the food web stability. Thus, they can have dramatic consequences. And finally, the next step is to apply the ecotroph model at global scale over the historical period of 1992 to 2021 to test ecotroph ability to represent the cumulative effect of past marine heat wave events. Thank you very much for your attention. If you have any questions, do not hesitate.
All right, great. Thank you very much. We do have time for a couple of questions. Any questions in the audience?
That was a great talk, thank you. Earlier in this session, I'm not sure if you caught the talk, we had Regina give the invited talk at the start where she spoke about compound climate extremes. And so I was really interested by your results here, and because you have that kind of ecotroph model coupled with the marine heat waves, is there scope to bring in other variables to see how a marine heat wave coupled with changes in productivity, coupled with changes in oxygen, might extend those recovery times or even decrease biomass even further? If you have any thoughts on that.
Yeah, actually it's a great question, and yeah, it could be done, yet for now the model is only forced by temperature and by net primary production. So if we would like to analyze this type of compounded event, we would have to incorporate another forcing variable as oxygen or pH or another one to see how that would impact in an additional impact or conjoint impact regarding the only effect of temperature on the marine on the model reaction. Yeah, it could be done.
All right, one more quick question.
Thank you for a thought-provoking talk. Just wanted to ask, so you mentioned that there would be particularly great impacts on predators of marine heat waves. And are there actually, based on observations, examples where that was really observed? I was just wondering if you came across that in the literature.
Yeah, actually there is. In the literature regarding observed marine heat wave, not necessarily, because usually high trophic level have the capacity of fleeing from the event, so they can like swim like a couple of kilometers from where the heat waves occur. Yet in historical, in experiment or in theory, there is like the theory of the guilt oxygen limitation, which have been already talked early in the week. It seemed that like higher trophic level and big fish, for example, taking this example, would be more limited regarding small fish to have to be able to give the energy necessary for the organism to face the new condition. So in the real life, not really, but there is some thought and some experiment analysis that goes in this sense.
Thank you very much. Our next speaker is Alexa Fredston.
Thank you. I like to name my papers and talks with declarative titles so you know what's coming, but I think you're probably going to want some more explanation. This project and a lot of what I do broadly falls into ecological synthesis, where we take data from a lot of different regions, species, time periods, and look for common patterns, or in the case of what I'm going to show you today, the absence of a common pattern. We haven't done that yet for marine heat waves in all systems. We do know for marine heat waves in sun systems like coral reefs from these types of synthesis projects that marine heat waves are really bad for coral reefs. We have some empirical thresholds beyond which we see consistent ecological degradation. And we have similar evidence for some other really shallow coastal systems. What I'm going to show you today is a version of that for demersal fishes, the much less glamorous looking ecosystems where many of us work, on continental shelves and slopes where a lot of our large commercial fisheries operate. Many of us, I think, intuitively imagine after a marine heat wave that you maybe lose some cold-affiliated species in a community, and that's related to a lot of the studies we've seen presented today about how close species are to their thermal niches. So if we imagine starting with a community like the one on the left, which has some cold-affiliated species, the blue bar, and warm-affiliated species, the red bar, and biomass is on the y-axis, but you could also imagine abundance or even species richness on the y-axis. You might think that those cold-affiliated species either leave or decline in performance or die. And that would cause, of course, a biomass loss. But that's not the only thing that could happen. You could also gain some warm-affiliated species. They might like this heat wave, and that could offset the biomass loss, but lead to a change in community composition. That can even happen if you don't lose the cold-affiliated species. You might actually end up with more species, more biomass than when you started. And of course, it's possible that marine heat waves don't have a generic impact either on biomass or on community composition. You probably see where I'm going with these. These are testable hypotheses that we now have the data to explore through combinations of historical biomass trends and historical community composition trends. I've been doing this with a wonderful working group called Fish Globe, which has been mentioned a few times this week. I am happy to answer any questions about Fish Globe. The short version is it was designed to harmonize all of the bottom trawl surveys done by federal agencies around the globe. This QR code and the link are for the data paper describing that by Aurora Moreau, who's been really the champion of this project. The project is looking for ongoing funding to maintain the database, but in the meantime, you can go download a ridiculous amount of trawl data that's very ready for large-scale biodiversity analyses that I'd love to talk to you about. The first analysis that we've done with it for an ecological question is this one. And from here on out, I'll ask that you not sort of tweet or publicly share these because this paper hopefully is very close to being published, but I'm really happy to send you figures, code, data, or anything else you'd like. I used the 18 bottom trawl surveys that are public and had enough data for this analysis. This covers, depending on how you define them, about 250 heat waves. Mike Jacox mentioned earlier that marine heat waves aren't new, it's just us studying them as a thing that's new. And in this about 30-year time series, we have a lot of heat waves. So to preview the results, I'll ask you, can you think of 248 case studies of marine heat waves having a really big impact on fish? I can. But it's a very comprehensive data set. We have Northeast Pacific, Northwest Atlantic, Northeast Atlantic, 45 degrees of latitude from the subtropics to the Arctic, and just an enormous amount of haul and species level data. The first plot I'll show you answers the biomass question. So on the y-axis here, we have biomass change. Any positive value means that we gained biomass from one survey to the next. Each dot I'll show you in a second is a single survey in a single year. The x-axis is heat wave intensity, and all of these results really don't change no matter what metric of heat wave you use. So you can imagine your favorite if you don't like cumulative intensity for some reason, or if the degree day thing is confusing. Here are the data. We really don't see any association between heat wave intensity and change in biomass. You are about as likely to gain species or gain biomass from one year to the next in a trawl survey as you are to lose it, regardless of how intense the heat wave was. And I'll point out that the huge scatter at the 0 is non-heat wave years, and that just shows you how variable trawl surveys and demersal fish communities are. To convince you that this is real, I've put up some of our most intense heat waves, which will look familiar to you, and I think illustrates this scenario, because we have the Gulf of Alaska up here in 2017, that's right after the blob, very intense, and you do see a biomass decline. But we also have the Northwest Atlantic after their heat wave in 2012, which some of the people in this room documented led to banner years for fisheries in places like the Northeast US and the Gulf of St. Lawrence. So you have evidence of negative and positive biomass effects, and lots of things sitting close to the 0 line where just nothing happened, even though there was a heat wave. You might be wondering, well, what if we just don't look at heat wave intensity and ask yes or no, was there a heat wave? There's also no difference. The red shows the heat wave years, but they're both centered on 0. You are as likely to have a biomass gain as you are to have a loss, whether or not there was a heat wave. So that's the biomass question. I'll quickly go over our results on the community composition change, focusing on this process of tropicalization, when you gain species from the equator that are relatively warm affiliated. On this plot now, every dot is going to be a species in a survey, so you'll see a lot more dots, but the y-axis is the same. So positive value, you gained biomass for that species, negative, you lost it. I'm sorting them by something called thermal bias, which is how warm affiliated they are relative to all of the species present in that survey on average. That basically means if you are like the one very tropical fish hanging out someplace temperate, you're going to have a very positive thermal bias. You're a lot warmer. And we'd expect you to have more biomass after a heat wave because you're probably very happy during a heat wave. The converse is true for cold affiliated species. Those are the ones we expect to decline. And I'm only going to plot heat wave years. So every dot on here was after a heat wave. There's absolutely no association here either. This beautiful cloud of points is color-coded by the heat wave intensity. Heat wave intensity also really doesn't have a relationship at this aggregated scale with what an individual species does in a trawl survey from one year to the next. We can, once again, aggregate this to the level of the community and ask, throughout all the fish in a single trawl survey, what was the average thermal niche? Was there turnover kind of an aggregate? And the answer is also no. We are about as likely with this index called community temperature index, which is basically a weighted average of all of those species level thermal niches, for the community to get warmer, positive CTI change, as it is for the community to get colder, regardless of whether or not there was a heat wave. So this came as somewhat of a surprise to us, but I actually think the more I think about it, the more it makes sense, because we have a lot of evidence that we can forecast marine heat wave events themselves from the physical environment, and a number of great talks on that this week. But we actually have basically no ability to predict the ecological effects of marine heat waves on demersal fishes. There have not been a huge number of documented effects on demersal fishes. The ones that have been documented are highly individualistic, and no general pattern emerges at the moment that we can use for prediction. I do want to point out that I think one of the obvious reasons for that is these compound events, which have been talked about a lot today. And that's one of the things that I'd love to do next, to understand why we see this pattern, or rather why we don't see a pattern that we expected. I tested a lot of things, thanks to reviewers 1 through 4, at least one of whom is in this room. And I won't leave the slide up for very long, but I'm happy to come back to it to answer your questions about some of the other things that might be predicting this. We looked at temporal lags, we looked at different marine heat wave metrics, different community and biomass metrics, a number of other predictors like latitude, traits, depth. The region-specific responses was a big question. So maybe some regions are gaining, others are losing, but they're all experiencing more change as a result of marine heat waves. We also don't find evidence for that. But I will say we basically have no statistically significant results. I've never had not even like a spurious significant result. This paper, which has like 100 models in it now. But when we do see a hint of a signal, it's always positive that you would get more biomass after a heat wave, which I think makes sense given that our data is heavily weighted away from the tropics. So there's a lot to do next, and I think this leaves us with more questions and interesting future directions than answers. Some of the things I'm really interested in is looking at new variables like compound events and other methods like machine learning, and also really zooming in on these most intense heat waves in our record to understand what made them unique. We know the heat waves that were documented as having huge ecological effects, but there have actually been heat waves that were that intense that did nothing. And therefore, we don't have a literature on those, and I'd love to understand why. So happy to take your questions, and I also wanted to mention I'm about to post an ad for a postdoc to work on quantitative stuff with me, so feel free to contact me about that or any of this. All of the data and code for this project are public or will be public very soon, so you're also welcome to just write to me and say you want the data, you want to play with it yourself. I'd love to share it with you and answer your questions. Thanks.
All right, thank you so much, Alexa. We're going to have a few minutes for questions for Alexa. Yes, I see an eager hand.
Thanks, Alexa, for the great talk. I wanted to ask, I know you put it up there, but you did look at bottom marine heat waves versus surface. And did you find exactly the same trend or at least somewhat of a difference? Because I would think that would help a little bit in theory.
Exactly the same trend. We have slightly more data when we use surface heat waves because the record goes back further. So we also did an extensive power analysis to see what biomass decline could we have detected with the number of trawl surveys we have. The answer is we could have detected about 8 to 9%. The DBEM model, which several people have presented on, including Natasha right before this, predicts a biomass decline of affected stocks of 6%. Those are still huge numbers. Like if every time there was a heat wave, 8% of the fish vanished, I think we might have noticed. But the main difference between bottom and surface heat waves is in the bottom heat wave record, there tend to be more heat waves that are, fewer heat waves of longer duration. It's just a slightly less dynamic place. So the number of heat waves changes, as does the data size, but the result does not.
All right, other questions? Okay.
Really great talk, Alexa. I'm wondering what other kinds of ecological responses you're considering examining, and in particular, if you've thought about, say, getting a tagging or telemetry data set and looking at behavioral responses during and following a heat wave.
Yeah, I would love to do that, and that'd be a really interesting follow-up. We didn't get very deep into traits. We did look by trophic level, feeding mode, and habitat. None of those kind of helped understand the results. But I think there's a lot more we can do. And in particular, sorting out, some of these groundfish live for a really long time but don't move, and their strategies during heat wave will be very different from others. So that's one direction that I think could really understand this. And as you see from the species plot, their biomass varies enormously from year to year. So there's so much going on besides the heat wave response. I think that behavioral stuff would really help understand it.
Yeah, okay. Thanks, Alexa. That was super great. Just a question, I know this is about heat waves, but if you change your heat wave metric, reduce it so that it becomes just temperature, average temperature, do you still see the same kind of, are heat waves worse than just average warm years?
Well, that's a great question. Do you just see more biomass in warm years or less biomass in warm years? We haven't done that, and we should. I'm writing that down. Obviously, this is a lot of what I work on is species on the move, and the inverse of that is, the inverse of processes like tropicalization is looking at a single species over space and asking, is it moving? And we know that that's happening in response to warming. There are also obviously a lot of community studies looking at turnover in response to more gradual warming. That's been done with some of these surveys, like in the North Sea, people have looked at, that's one of the surveys in here, and they have looked at turnover. We haven't done it in the full fish globe data set, though.
Okay, we might have time for one more quick question.
Thank you. In addition to your question about temperature, I would suggest try ocean heat content.
Ocean heat content, thank you. That will go in the compound paper.
Oh, sorry. All right, thank you so much, Alexa.
Thanks.
Great talk. Okay, so I am very sorry to report that the 2:30 talk has been canceled. So we're going to use 15 minutes for open discussion, questions for earlier speakers that you didn't have a chance to ask during their talks, those types of things. So do we have any? Let's start with any questions for earlier speakers, if anyone has anything remaining. Yes.
I have another question and suggestion for Alexa. I'll let you be organized. I was just wondering if you were examining also the thermal range of the species for those specialists or generalists in terms of temperature, and also as referring to depth as a continuous variable, not just surface or bottom. I'm not sure what you've done.
Yeah, so the first one, I have not looked at, one of the things that oh, sorry. Thanks. Yeah, one of the things I'd love to do in the future is look at whether the biomass response is predicted by the thermal safety margin of the species being exceeded by the specific heat wave. We have not done that. I'm very curious what we'd find. We used just the average depth of the survey as a predictor within each one to see does the biomass sort of just vary by where this survey was done. And that's as far as we got with depth. Again, something we could explore a lot more.
All right, thank you. Any other speaker-specific questions?
I'm going to ask Alexa another question. You're lucky to be right before this pause, but I actually noticed, well, I will just say that, you know, my students' work looking at just the Northeast U.S. backs up what you found too. But I noticed when you were looking at the biomass change versus the magnitude of the heat, like it seemed like the most extreme heat waves, the biomass either increased or decreased, and there's not many around this area. Did you notice that too?
Yes. I'm not mic'd up anymore, so I'll steal the mic back, sorry. Yes, that slightly changes with the marine heat wave metrics, so some of that happens to do with the most extreme ones. There are also some kind of interesting intersections. So we see if you remember at the left side where there's just a huge scatter of those points, a lot of those are from smaller surveys, so there is more stable biomass over time in bigger surveys, just bigger sample size, less variability. We control for that in the models, but not in the plot. And so some of the surveys that have recorded the big heat waves happen to be really, quote, good surveys. And so they're kind of, they do show a change. They don't show a super extreme change, probably because of variability. They're a little bit constrained. So I think that's kind of just due to the data.
Thank you. All right. I'm going to switch gears to make sure. I think that we have lots of great questions for Alexa, but I want to be sure to broaden the conversation. So do you have a question that goes to a different person?
This is different parts of the day. This is a question for Mike Jacox. Great talk. The question is, do you have a sense if there is predictability on longer timescales, multi-annual, decadal timescales for heat waves? And if there's a use for it with stakeholders, do they care about 2 to 10-year timescales? And that's maybe a question for other people.
Yeah, I can speak to the first part better, and then probably this room can speak to the second part a little bit. Yeah, so we haven't looked at that explicitly for heat waves, and I don't think anyone has, but again, it's just temperature, right? And there have been multi-year forecasting studies that have shown in some regions SST is predictable beyond a year. I think I think it goes into year 2, as opposed to some biogeochemical variables where there's suggestion that it might be really years in advance. But yeah, I think you can definitely get into year 2. I don't know. I feel like there are people who could take on the decision-making piece of this better. I'm looking at Kathy, but others too probably.
Well, I was looking for Jason because he might have insights on that too. But I think that, I think that long term, once you start getting into decadal, you're kind of moving into more strategic management and planning rather than sort of the tactical short-term management. So I think that there is already sort of a general awareness of long-term increase and change in conditions that, this is a part of, and it's really important to bring that in as well. Jason, do you have anything you want to add based on your experience?
Sure. Excuse me. So definitely agree with Mike there that the year 2 signal is predictable. If you couple that with like a big driver that has like a 9 to 12 month lag in it anyway, you can say something about year 2. The decadal work is, I think, still pretty much in its infancy, and wouldn't want to say too much about what you might get out of it, but definitely providing insight into the longer term strategic decision making about where you might operate is something that we'd be looking to at least provide some kind of insights on.
Great. All right. Yes.
Yeah, hi, Jan Newton, University of Washington. I work with Samantha Sidlecki out of the University of Connecticut. I don't know if she's in the room, but anyways, hi, Sam. And so she's worked on models of many different time scales, daily as well as seasonal, as well as end of century. And I think that we've had great success working with decision makers, especially when you involve them kind of on the ground level and show them some comparisons to data that they know they trust. But one thing that we do hear from a lot of managers is like they want to know the 5-year, the 10-year time scale, which I think is a really hard thing to do for models. But I just wanted to relay that I think that we're making some good progress on these shorter terms and the longer terms, and yet that one looms unattended.
Yeah, and I'm just going to throw in a comment here because hopefully it'll bring in one of our other speakers. I think that yes, there's often interest in these timescales where we have a really hard time getting things right, and there's also real risk when we get things wrong. And so I wanted to come back to Emon to speak, if you can add on anything to your talk when you mentioned that, fishers resorted to using their experience, to using their own knowledge, because sometimes the forecast for bad conditions weren't right, and how that interplay is occurring, whether they always rely on their experience or whether it's completely eroded use of the forecast or whether it's a mix of the two now.
Okay, so the weather forecasting management system in Bangladesh has improved over the last few years, improved so much better. But the fishers' decision-making strategy is somewhat different in the field. So they keep their radio when they're in the sea, but do not want to use that because they believe that the weather signal provided by the government is not the true signal in the sea. So they believe that they know the sea much more better than the government. So even if the weather signal is like a cautionary stage, they do not want to come to the shore immediately. They want to understand. They look up at the sky. They look the movement of the fish species. So when they observe some kind of, as I shows in the presentation, that when they observe the movement of churi fish locally, I cannot say the English term of that fish, but when they observe that kind of movement, they see they see lightning in the straight sky. So at that time they decide, okay, it's time to go at the shore now. So it's kind of a mixed thing, but they are forced to come to the shore when the Coast Guard tells them, okay, do not stay right now, go directly, because otherwise they'll be forced or sent back to the jail. So, that still, it would be mixed criteria to decide whether to go back to the shore or to remain in the sea. But overall, the weather forecasting has improved a lot, but lack of GPS system and that small-scale fishers cannot afford that. It's very expensive for them. Even they cannot take life jackets and other that initiatives, they cannot actually do that actually because of the lack of capacity. But they try, and still, the greed of catching more fish during storms and other extreme events, so that do not actually let them change their decision to go back to the shore. So they try to remain in the sea and to get back when they reap a good harvest from the sea. Okay, thank you.
Thank you for elaborating. Great. Any other questions or discussion points people want to raise? Yes.
Actually, I have a question for the second talk of this afternoon. Yes. If you just focus your analysis for the short-term marine heat waves, those that span 1 to 2 months, how does that affect, or maybe do not affect, your conclusions?
Thank you for your question. Well, actually, from the literature, I could show that marine heat waves lasting less than 2 weeks or 1 month should not have ecological consequences. And then, well, the model reacts the way that if there is no other perturbation, he goes back to the normal by every time step. He goes back slowly to the normal. Yet, if your question was at long term, how do we interpret small marine heat waves? How do we follow them at long term? Well, as last figure I show, we can see how the different compartments react differently, and depending of the trophic level of species, they have different metabolism and are able to reach back their ability to live in their common habitat, and then they are able to reach back their original states. Yet the only thing that we didn't have, and that could be added, and it's the objective of the next step of the study, is to add the historical trend of marine heat waves, and then we will be able to follow how the frequency of marine heat waves affect the response regarding one-off event, and see how several marine heat waves could add up different effects regarding time. So yeah, we will be able to follow how different marine heat waves at a small time step will add up at longer time step.
All right, great. Yeah, Mike.
So I have a thought which is, I think, really based on Natasha and Alexa's talks taken together, which is, all this hubbub about marine heat waves. Maybe we should really be talking about productivity waves. And it's next to sea surface temperature, one of the best observed things. We have 25 years now. And so maybe we all want to get in on the ground floor of the next HAB et al. 2016 marine productivity droughts or something like that. And as an explanatory, for change.
Nice. And I think Regina has a response.
I just want to add something that Tatiana Ranson from GSO, University of Rhode Island, did a study that shows that the phytoplankton when you have a warming, particularly in the tropical oceans, change. There is winner, species win and losers, but the winners are low in lipids, which is much more rich in nutrition. So in terms of a biomass, you don't have a change, but you have a change in the quality of that biomass in a base of the food change. So I don't think it's just numbers. That's why I think you should have to have more regional studies that then you can analyze at that kind of a level too.
Great, that is an excellent point. Thank you all for the good discussion. We are going to move on so that we stay on time and in sync with the other sessions, but I hope that you'll also continue talking with one another during the coffee break. So our last speaker is Julie Keister.
Thank you. Is this on? Yeah, great.
Okay, thank you. I'm going to be talking today about 3 case studies of how heat waves affected juvenile salmon through the bottom-up processes that include zooplankton. And so these 3 systems shown, I'm going to start by contrasting Puget Sound and the California Current system. These are 2 very different systems. Puget Sound is an inland fjord. It's separated from the ocean by a series of shallow sills, so it's a very retentive system, whereas the California Current system is a classic upwelling system. And then I'll bring in a case study from the northern Gulf of Alaska, which has been published, and another contrasting system. It's a downwelling system, but because of the complex topography of the inland waters, there's a lot of local influence on upwelling and nutrient delivery. So the question is, in these 3 different case studies, do we see coherent responses of the effects of heat wave through zooplankton to salmon, or are there important differences that could inform us about lessons learned or how we should be managing them differently? So briefly, methods. I'm not giving you many methods. These are published for both of these monitoring systems, but they have very, very similar time series observations protocols, so it makes it really easy to compare them directly. In Puget Sound, the monitoring in Central Basin began in 1997 just for hydrography and chlorophyll. My program brought in zooplankton sampling starting in 2014, which was the year that later in that year the heat wave actually hit. So we don't have a lot of data before the heat wave, but we have 2014 and on. Whereas in the California Current system, they started their full program in 1996. The the salmon data for both of these programs, I'm going to be showing you coho survival data. These are calculated from hatchery coho that were tagged, and so there's a very good estimate of the number of hatchery salmon that were released and the adult returns, so we get a very good smolt to adult ratio that's the survival of those fish. And they're provided either by the Washington Department of Fish and Wildlife or from a public database, but it's the same type of calculation. Okay, so to move into the actual data, first showing you the California Current system. Each of the red boxes that I'm going to be showing in these slides is going from the beginning of 2014, so just before the heat wave impacted these systems, through the end of 2017, which is when the heat wave mostly had been started to dissipate, if at all. The California Current system in that top panel, it shows the very classic, we know this pattern now. The heat wave hit pretty hard. It lingered for several years. In this region, it was intermittent, but mostly very positive anomalies. What was not quite so intermittent was the nutrients. They were very strongly depressed throughout this entire series, except for some very brief periods when there was some upwelling winds in the middle of summer, but a very strong negative anomaly of nutrients through this whole time. And that's not quite as clearly reflected in the chlorophyll, although 2015 was quite depressed. There was still some chlorophyll during this period. So it's not a complete suppression of the system, but it's definitely overall not strong chlorophyll anomalies for certain. And the really strong signal in the biology is in the zooplankton, which did show very strongly depressed anomalies throughout this period. So this seems like a classic bottom-up process from the temperatures and nutrients to the zooplankton that was driven by the advection of warm ocean Pacific water into the California Current system and suppressed that whole upwelling system for a while. Now in Puget Sound, again, the temperature anomalies are pretty classic. In this case, there's no intermittency though. Once it got warm, it was warm. It's a very retentive system. And even though it looked like in 2017 we were getting some return to normal, really the system retained a lot of heat for several years after the actual heat wave. Our nutrients, in contrast to the California Current system, really were not severely depressed. They're a little bit anomalous, very intermittent, but compared to the rest of the time series, they're kind of average. And that's also reflected in the chlorophyll anomalies. There was some strong periods of negative anomalies, but there was a lot of chlorophyll. There were some pretty decent spring blooms and fall blooms, and the chlorophyll does not show a very strong suppression. And what was surprising to us when we got our zooplankton data was that, in complete contrast to the California current system, in Puget Sound, we saw elevated biomass of chlorophyll. And we know from the species composition that this was elevated across all of the crustacean taxa: crab larvae, amphipods, krill, especially copepods. All of these things that really feed a healthy food web were elevated during this period. Turning to the salmon survival here in the California current, these are survival rates from 1998 to 2020. And in the California current, it was pretty clear that these are some of the lowest numbers in this record all the way through the heat wave. So that's not surprising given the zooplankton biomass anomalies, but it's an evidence that the zooplankton were not getting enough food to sustain their metabolic increases during that warm period. In Puget Sound, I have 3 examples. We have a whole lot of rivers and stocks that go into Puget Sound that I have data for all individually. So I'm just showing you 3 here as an example of the variability that we saw in the system. But some of what we saw was elevated coho survival rates. This example, Baker River coho, this is a river that it's part of the Skagit system. It goes into Whidbey Basin. There were negative, pretty bad anomalies in survival in 2014, but really there was elevating, increasing survival rates throughout that heat wave period that matched very closely that zooplankton biomass anomaly that we saw. On the other hand, Big Beef Creek was pretty flat. There just didn't seem to be a whole lot of anything going on in the survival rates during that period. And the Skykomish River, which is another river that enters into the Whidbey Basin, that actually showed pretty low survival rates during the heat wave, but they started in 2013 and didn't recover after, so it's kind of not clear whether the heat wave was the biggest influence on this or whether something else was going on. So definitely a difference between these 2 systems, but also a lot of variability. And these 2 systems, I've already said a lot of this, but we think it's really because they're fundamentally different systems that these processes were operating differently. Puget Sound being always a warm, relatively stratified system compared to the California current. Nutrients are really, we know from a modeling study that nutrients were not seriously depressed during the heat wave, and tidal mixing is what brings them up to the surface layer to get to the primary production, and that is independent of climate change. Whereas in the California current system, it really needs that upwelling system that was shut down to deliver the nutrients. And so big differences in those 2 systems. So to bring in then the Northern Gulf of Alaska, this is a study that Rob Surian led with many, many co-authors. They compiled dozens and dozens of time series and did a dynamic factor analysis on them to look at the patterns in biological response to the heat wave. But starting again with temperature, the classic signal, very big anomalies, very persistent through this period. And so what I'm going to show you in each of these plots from their paper is results of the dynamic factor analysis, but also individual observations. So each of these lines is results of the model over the entire period that they show of 2010 to 2018. It's informative, but what I really want you to look at is the single points, because then we can look just within the marine heat wave years. And so in this particular example, this is phytoplankton. If we look at the black dots, which are satellite chlorophyll biomass, so surface biomass, and the red dots, which are actual cell sizes of the phytoplankton, we see a bit of a mix of changes in the black dots, the total biomass, but we see a really strongly decreased cell size during the heat wave, which should indicate some large trophic changes. And since it's still a little messy to look at the dots, I put the main point over here on the right for you, for each. In the zooplankton, the dots are blue for cold water species and red for warm water species, and cold water species, we just heard from the audience, tend to be lipid-rich, larger, better for the ecosystem in general, and warm water species tend to be smaller and less nutritious. In this case, both were either neutral or positively anomalous during the heat wave, and that was, again, a bit of a surprise, especially when looking at the cell sizes. In this system, forage fish are really important in the diets of the juvenile salmon. So I'm showing here especially capelin in black dots. They were strongly depressed during the heat wave, so that could be bad for juvenile salmon. It also could be what released the zooplankton from grazing pressure. So there could be a mix of top-down and bottom-up processes in this system. And then finally, I don't have actual survival rates for coho in this system. What we have is fishery catches, and so it's a bit of a decoupling of the processes. It's a little harder to link them directly. And also the timescales are a bit different because you're harvesting the adults and they would have gone to sea the year before. But what we see is, we can move on past Chinook and look at the red dots, which are coho. They were low before the heat wave, but got even lower during the heat wave, and then a big rebound. So the later couple of years during the heat wave would be from the outmigrants during the heat wave. But then the 2017, this fishery would have been from juveniles that outmigrated during the last year of the heat wave. So again, a little bit of a mixed signal there, but maybe not so bad for coho in this system. Compared to the Chinook, which if you've been looking at those black dots, they really did quite poorly during the heat wave. So in conclusion, the take home really is that we cannot just generalize the impacts of these, the heat waves on these systems. It's not always bottom-up processes, and even when it is, it doesn't always go the same direction in these systems. The individual systems are really important to consider, and especially when you look at just temperature as a proxy, because really the temperature records sort of showed the same thing in all of these systems. So these long-term monitoring programs are really necessary to observe these changes and inform ecosystem modelers. And we need flexible and adaptive fisheries management in order to account for these lower trophic level changes in our fisheries. So that's it. I'll just leave this as thanks to my funders.
All right, thank you so much, Julie. We do have time for a few questions or comments.
Hi, thank you for the lecture. I was curious about the way zooplankton were sampled, because I know it's really an issue and they're really patchy, and how did you handle it in this study? Just curious.
Yeah, we mostly took them as they were sampled. So for the California Current and Puget Sound, they are, the data that I showed were vertical net tows sampled biweekly at the same station. And so it's just the average zooplankton biomass from each of those that formed the time series. For the Northern Gulf of Alaska, that was a CPR survey, and I was not a co-author on the paper, so I don't know exactly how they handled those, but I believe they did some averaging of the whole chunks of the CPR lines to get the biomass of the different types of zooplankton.
Thank you.
All right, other questions? Anyone? Well, I was thinking that Mike Jacox left, but there may be some merit in the way that you have looked at this to think about his idea of productivity waves, because it seemed like you were getting quite a lot of more distinction there than with just temperature.
Yes, more confusing too. It takes modeling, I think, to figure out all the patterns, but yes, there were a lot of changes in production, and how it cascaded and didn't cascade through the system was interesting to try to follow. Yeah.
Sorry, I thought you had another question, but I think I stole her question. Oh, great, Mike.
Thanks, Julie. Great talk. I was wondering about your sort of take-home point about the need for adaptive and flexible management. And have you thought at all with the sort of 3 different outcomes in these systems, if there's any, if there would be any advice for different management approaches based on that?
Well, so my knowledge of Puget Sound and the California current are better than the northern Gulf of Alaska, but I would say that the lesson specifically for the Puget Sound managers is to stop using coastal indices as the predictor of the ecosystem shift, because that's what had been happening until we started the monitoring programs in Puget Sound. We assumed there would be coherent responses between those systems. And so they really need to develop their own local indices and do their own monitoring, which they've started. In the northern Gulf of Alaska, it was hard to find time series that were of the resolution and length and measuring multiple variables that really make it easier to distill the mechanisms. And so I think that one of my recommendations, not necessarily for how to manage the fisheries, but how to inform the fisheries, is to have more consistent and integrated monitoring.
All right, thank you so much, Julie. All right, and thank you to all the speakers in this session. We'll resume at 3:30 for our last set of talks. Thank you.
Hello. Can everybody take a seat, and is Haila here? I'm sorry. Oh. Are you Haila? Haila, great. All right. Do you have you're all set? Okay. Hello, everyone. Could you please take a seat? Our first speaker this afternoon is Haila Schultz. Welcome.
All right, hi everyone, thank you so much for being here. I'm Haila Schultz, I'm a graduate student at the University of Washington, and today I'll be talking about jellyfish impacts on the ecosystem. So first I want to acknowledge that this work was conducted on the unceded ancestral lands of the Duwamish people and the shared waters of all the tribes and bands within the Coast Salish, Squaxin, Puyallup, Suquamish, Tulalip, and Muckleshoot nations. So if you're not familiar with moon jellyfish or Aurelia, this is them. They're a miroplanktonic scyphomedusan that can reach up to the size of a dinner plate. And one of the main things about them is that they aggregate in really large groups. So you can see in this video, there's a bunch of individuals hanging out together, and that's typically how they exist. Aurelia, the genus, exists in coastlines all over the world. So anywhere you see color or gray dots, that's somewhere where Aurelia is found. Today I'll be talking about Aurelia labiata on the western coast of North America. And our study site is in Puget Sound in Washington. So Puget Sound is a deep fjord-like estuary with kind of 5 main basins. And in Puget Sound, jellyfish, especially Aurelia, tend to hang out in these shallow finger-like inlets in South and Central Puget Sound. To give you kind of a better look at what these aggregations look like, this is a 78-foot, I guess 25-foot meter boat. And each of these individual dots you can see is one jellyfish. So there's easily thousands of individuals in this frame, and these aggregations span farther outside of this frame, so they're pretty amazing to look at and witness. As we all might know, there was a heat wave that affected the western coast of the United States, and it went into Puget Sound. So this is Salish Sea, and Puget Sound is in the bottom right corner of these panels. And you can see it's kind of developing from 2014 to 2017. And if we zoom in on one of these panels, you can see that in Puget Sound down here, these finger-like inlets are where most of the heat wave, where the heat wave had its highest amount of change. So we can actually see these from the air, and what people noticed during the marine heat wave was that they noticed larger jellyfish aggregations, more abundant jellyfish aggregations, and longer persisting jellyfish aggregations in these areas. So this is an aerial photo from Bud Inlet, and each of these white streaks here is a jellyfish aggregation. Our intern, Lucy Rusa, measured the area of these aggregations using aerial photos and found in 2015 and 2016, during the heat wave years, there were elevated areas of jellyfish compared to the normal year of 2013, kind of confirming what people were seeing with their own eyes. In addition to these shorter-term heat wave events, there's expected to be longer-term change in jellyfish associated with climate change. So these are many different taxa of jellyfish in Puget Sound, and Aurelia are kind of the winners in these climate change scenarios. So this is work by Corey Green. And he projected that using future temperature and salinity and land use, a doubling in the probability of Aurelia presence by 2095. So we're kind of interested in what increasing jellyfish populations what impact they might have on the ecosystem and also the food web. So this is your typical Pacific Northwest food web. And we do know that jellyfish are voracious predators of zooplankton. Zooplankton, which are these really important links in the food web, transferring energy from phytoplankton up to the higher trophic levels. So to answer the question of what the impact that jellyfish might have on ecosystems, we conducted experiments, fieldwork, and modeling efforts. For our experiments, we used plankton toes to collect natural zooplankton assemblages. And we also cultured Aurelia in the lab. We then split the natural zooplankton assemblages up into multiple tanks and put varying numbers of jellyfish in those tanks, giving us a gradient of jellyfish biomass. After 2 hours, we removed the jellyfish and measured all of the remaining zooplankton to get an idea of how much food they were able to eat during that time period. Here's just some data on their selectivity. You can see on the y-axis we have various zooplankton taxa, and they seem to be eating mostly crustaceans or selecting for mostly crustaceans. And today I'll be focusing in on these two copepod species, which were the two most abundant taxa that were found in our samples and our fieldwork. So that's medium calenid copepods and the cyclopoid copepod Digicocoreus anglicus. Here's some data from our experiments. We utilized generalized linear models to track the consumption of copepods during our experiments. So on our y-axis, you see copepod density that was left at the end of the experiments, and the x-axis is Aurelia biomass. And so you can see they were able to rapidly remove copepods from the tanks in just 2 hours. And we found that in 2 hours, Aurelia at high densities removed up to 73% of the copepod stock. So we wanted to go into the field and see if this pattern held. So we visited 4 different inlets in Puget Sound. These 2 inlets that had jellyfish at the time of sampling and 2 inlets that did not have jellyfish at the time of sampling, but oftentimes do, so we were able to compare those. And we collected data on jellyfish, zooplankton, microplankton, nutrients, and CTD data. So we wanted to see what factors were affecting these 2 copepod taxa, and made several models incorporating different environmental factors. And we found that in the best models, Aurelia was a predictor for copepod biomass for both of these species. So similar to our experiments, we found that at higher levels of Aurelia biomass at the field, we see declining copepod densities. And this gives us an indication that they are probably noticeably eating the zooplankton in their immediate area and depleting the zooplankton stock. So in the field, we found that copepod densities were up to 75% lower inside of the aggregations compared to outside of the aggregations. We also wanted to see if there was some type of trophic effect of this predation on zooplankton. So on your left, we have phytoplankton, dinoflagellates, and diatoms. And these blue bars are inside of the aggregation compared to the green bars outside of the aggregation. And we found, although there was a lot of variation, elevated abundance of diatoms and dinoflagellates inside of the aggregations compared to outside of the aggregations. And this could be happening due to a few factors. So it could be that the jellyfish are eating enough zooplankton to release the phytoplankton population and allow them to grow because the phytoplankton aren't being eaten as much. Or it could also be due just to the presence of the jellyfish in the area. So on the right, we have our microplankton or phytoplankton communities, and you can see the blue and orange, these are the inlets that didn't have jellyfish at the time of sampling, and these two are the inlets with jellyfish. And the communities were separated, and they were separated along an axis of difference in nutrients. So in our jellyfish inlets, there were elevated levels of nitrate and nitrite, which we both know are important nutrients for phytoplankton. So we speculate that the presence of jellyfish could be leading to increases in these nutrients. So jellyfish release a lot of ammonia, and we know that on the surface of jellyfish, bacteria convert this ammonia to nitrate and nitrite. So that could also be restructuring the phytoplankton communities and leading to increases in inside of the aggregations. But to really get an understanding of what the impacts might be on the community and on fish especially, because we don't know if the jellyfish are competing with fish for zooplankton prey. We are utilizing the Atlantis ecosystem model. So my co-authors, Nalini Mazzari-Luna and Isaac Kaplan, are working with the Atlantis ecosystem model for Puget Sound, which has multiple different biological parameters and also an oceanographic submodel and a human impact submodel. And we're using the data from this study to improve the Aurelia labiata functional group within this model. So here are some of the data inputs that we're giving to the model to improve the model parameterization. So for our experimental component, we are adding the maximum consumption rate of copepods, as well as the maximum consumption rate of zooplankton in total. The electivity indices I showed you earlier for an idea of species selection, and Aurelia labiata growth rate, which we got when we were rearing the jellyfish. And then for the field component, we are adding the maximum Aurelia labiata biomass in situ that we found during our field sampling, and also the depth distribution in the water column of the jellyfish that we found. So using this model, we can actually test the effects that these jellyfish will have on the food web, testing scenarios like the sensitivity of the food web to a range of jellyfish abundances, including future increases due to marine heat waves and longer-term warming, the impacts of a potential new jellyfish fishery, and also the impacts of trophic cascades. And additionally, we can also test the potential competition between fish and jellyfish for the zooplankton prey. So for just a quick summary from our experiments, we found that Aurelia rapidly consumed copepod prey. Aurelia aggregations were associated with decreased zooplankton, increased phytoplankton, and increased nitrate and nitrite. And we are currently working on the modeling to update the Aurelia parameter and examine the potential ecosystem impacts of climate change on the Puget Sound ecosystem. And with that, I'd like to thank my collaborators and everyone who was involved in this work, and I'll take questions.
Are there any questions? Great.
Hi, thanks, Haila, for a great talk. I don't know too much about zooplankton, jelly behavior, but how do they actually select for certain zooplankton prey over others? Like, is it olfactory or sensory, or like, how do they know?
Yeah, I think there's not a lot of, physical features that they have that help them select, but they can select by the way that the different zooplankton, like how it moves to their stomachs. Also, certain plankton, I think in our experiments, like the heavier plankton, maybe the ones with shells, may have sunk a little bit more, so maybe they weren't able to eat those as much as the ones that were swimming around. But yeah, so we're not totally sure, but we do know that they eat a lot of crustaceans.
Great. We have time for one more question.
Thank you for a great talk, Haila. You said you're going to work with people on the Atlantis model. Do they have data, or any fisheries people have data of fish that eat the jellyfish?
That's a good question. I think that is definitely something that they're planning on including in the model. In Puget Sound, there aren't a lot of natural predators of jellyfish, but there are a few. So that is something that's going to be incorporated.
Great. Thank you. Next, we have Mike Litzo.
Thanks. So the project that I'm going to present today has as its goal what we want to do is we want to use the tools of ecosystem science, and we want to use the tools of climate science to provide information for a group of fisheries stakeholders who are making decisions in a real crisis environment. So this study was motivated by an unexpected large magnitude fisheries collapse that occurred in a fisheries system that didn't have a lot of anticipatory adaptive planning in place. And while we coordinated and consulted with stakeholder groups as a part of this work, and we also presented the results of this work into the management process as scientific advice, I'm not going to talk about those parts of the study today, but I'm going to talk about the thought process that went into the information that we generated. So this is the study system. It's the Eastern Bering Sea snow crab fishery. It's a winter fishery. Until recently, exploited a population that was very abundant, with a population that was estimated in the tens of billions of animals. The market value for this animal is very high, so it was a very lucrative fishery. Then the fishery collapsed. From 2018 to 2021, the total abundance of the stock went down by more than 90%. This left-hand plot just shows the component of the fishery that are the legal-sized males. There are so few small animals left in the population growing to legal size that legal size abundance continued to decline into 2022 to the lowest abundance we've seen in the time series. The fishery is closed. Our most optimistic expectation is that it'll be closed or we won't see appreciable recovery for at least 4 or 5 years. As recently as 2021, this fishery was worth almost $2.5 million per vessel for a season that lasts like 6 to 8 weeks. So an incredibly huge economic hit from this closure. And then on the right, it's not coincidental to the story that this occurred following a period of unprecedented warming in the Bering Sea. So in 2018, stakeholders in this fishery were borrowing money to increase their ability to participate in the fishery. And now, just a few years later, these same stakeholders are making really different decisions about how long they can hold on, how long they can stay in the fishery, how long they can maintain their abilities to participate in the fishery with the hopes that recovery will be coming soon, versus versus another strategy of having to walk away and sell out at pennies on the dollar. So as we're trying to react with our group of colleagues and come up with information that could be helpful for stakeholders making these decisions, we dipped into the social sciences literature on human cognition and what makes for effective adaptation. And it's a big and really interesting literature, and I'll just hit a few high points here. The main thing is that effective adaptation requires stakeholders to recognize, attribute, and anticipate change. So that's how we're going to organize our study. For the recognition step, we're going to build a model that attempts to place the snow crab collapse in the context of overall ecosystem change in the Bering. For the attribution step, that's really important here because that warming, if it was part of the large internal variability that does affect the Bering Sea, that's not predictable going forward. But on the other hand, if it's the anthropogenic change, that is fundamentally more predictable. So that has real implications for adaptation planning. And then in terms of anticipation, we're going to try to estimate climate risk for this fishery historically in the current climate and over short timescales going forward that are relevant to adaptation decisions. And then just the last thing I'll say about that cognition step or that cognition literature is that complexity can be the enemy of effective decision making. And the complexity of our advice can be a real barrier for stakeholders. So we really tried to keep our advice empirically robust but simple. So we're going to start off with this recognition step, and we want to build a model that explains the collapse of the fishery in terms of ecosystem change. We start with the observation that snow crab are an Arctic animal. They have a circumpolar distribution. They're found in Alaska in seasonally ice-covered waters with temperatures less than 2 degrees. And high-quality habitat and the population goes up into the Arctic Ocean in Alaska, but those animals are too small-bodied to be exploited by the fishery. The animals that grow large enough to be exploited are at the southern edge of the fishery, and that's the part of the population that collapsed. So if we're talking about an Arctic animal exposed to rapid warming that's collapsed at the southern edge of its population, of course we think in terms of borealization. This was set up really nicely by the keynote talk at this conference. Typically, we think of borealization in terms of community ecology, but in this study, we're going to define it a little more broadly. We're going to define it as the transition from an Arctic physical and biological state to a subarctic physical and biological state. And then we're going to ask the question as to whether this snow crab population collapse was a consequence of borealization in the system. So to do that, we have to measure borealization. We have to produce an index of borealization over time. And this is a really well-studied system. So there's all this knowledge that we can lean on, all these different characteristics that should describe the difference between Arctic conditions and subarctic conditions in the system. And conveniently, a number of those with the stars are characteristics that have been proposed as proximate mechanisms that led directly to the collapse. It's a data-rich system, so we can get time series for these characteristics, but we don't want to use the individual time series in our analysis because they're noisy, they're prone to observation error, they tend to be collinear. What we want is an overall measure of how things have been either more Arctic or more subarctic through time. And we do that with a dynamic factor analysis. So this is just a method that allows us to identify an unobserved trend that's shared across all those different time series. And so the model expresses loadings on, or calculates loadings on individual time series. So for this model, more Arctic ice-covered conditions have a negative loading. Conditions that reflect warmer, more subarctic conditions have a positive loading, and then we get this shared trend across all the time series that gives us our index of borealization over time. So again, negative values are more Arctic conditions, positive values are more subarctic conditions. So we want to take that borealization index and we want to ask statistically, does that explain the collapse of the population? And we do that with this Bayesian regression approach, and we fit our models, these regression models, separately to the female and male components of the population. And that's because there were some different trajectories for the two around the collapse that suggested the potential for different responses. But in fact, we found it's a pretty similar pattern where you have sort of insensitivity to borealization, increasingly subarctic conditions until you reach an apparent threshold for both sexes. And then you see that negative impact on the population. And while the math and the statistics that go into this analysis are sort of complex, the endpoint, I think, conveys is how to put it. It's simple enough to convey to stakeholders and managers this story of understanding that this negative consequence for abundance of the population as a part of this ecosystem change. So then we want to move on to attribution. Again, because it's really important for planning as to whether this was internal climate variability that we can't predict going forward, or if it's the anthropogenic trend that's much more predictable. So to answer that question, we're going to calculate the fraction of attributable risk, which is the most common attribution statistic that's used in the climate literature. And it just expresses the proportion of risk for a given event that's due to human activities. And we're going to calculate that statistic from output from 23 different CMIP6 models. We use this model weighting approach that's important for evaluating sort of the skill and independence of the different models that you bring into this analysis. But of course, we can't get our borealization index out of these Earth system models or climate models. These models don't have time series for Pacific cod abundance in the Bering Sea or hematodinium disease in the Bering Sea. But remember, borealization is fundamentally just an expression of warming of the Arctic. So we can use temperature as a proxy for borealization in this attribution step. So to do that, we first of all plot borealization against sea surface temperature anomalies, and we confirm that there's that one-to-one relationship that you see there, or close enough for government work, kind of one-to-one relationship. And so we'll use temperature as our proxy for borealization in the attribution study, and then just note that these most extreme values of the borealization index that we've observed to date coincide with temperatures greater than 4 standard deviations above the pre-1950 climatology. That becomes important a little later in this story. So this is what we get for that attribution part. We've got the fraction of attributable risk for annual sea surface temperature anomalies from 1950 to 2021. Now we've got it for 2022. And this gives us an expression of the trend of human influence on the system. And so a FAR value of 0 indicates a temperature that's equally likely with or without human activities. A FAR value of 0.5 indicates temperatures that are twice as likely because of human activities. And then in these really warm years where we saw those really high levels of borealization, and then when we saw the subsequent collapse of the snow crab population, those FAR values were above 0.999. And so that corresponds, there's a related set of temperatures where you can calculate your estimate of how much more likely temperatures are due to human activities. So that corresponds with temperatures that are hundreds or thousands of times more likely due to human activities. So clear evidence that these extreme temperatures, this rapid borealization, and then the subsequent collapse is due to human activity, and gives us predictability going forward. So that predictability going forward loops in with the last stage of the study, where we want to evaluate climate risk in a way that is communicable to managers, to stakeholders, in terms of how much things have changed and how rapidly they seem to be changing. So to do that, we're going to calculate temperature probability distributions from those same 23 CMIP6 models, with the model weighting applied the same way. And we're going to look at those PDFs in different climate states defined by how much North Pacific warming's occurred. And we're going to note that critical threshold of 4 standard deviations. So all the way from the pre-industrial state, all the way up through a degree of warming, those 4 standard deviation events remain incredibly rare, as you would expect for a 4 standard deviation event. But this is the climate we're in now, between a degree and a degree and a half of warming. And our calculations are that we should expect an event that big about 1 year out of every 6. So that's the current climate. And then looking forward, once we cross over a degree and a half, which under SSP 245 is about the 2040s, we should expect those magnitude of warming that greater about every year out of 1 year out of every 3. So we haven't made any inferences about the likelihood for this fishery to migrate farther north, and that's an important part of the adaptation piece. But what we have shown is for the traditional fishing grounds for this stock, the climate risk has already increased greatly. And we expect it to continue to do so rapidly. And that really means that stakeholders who are basing their assessment of risk if they're calculating their assessment of risk based on their lived experience, they're opening themselves up to vulnerability. That's a real source of vulnerability because that historical experience is really no longer applicable in this system. And then we sort of, as we developed this idea, this approach, we really thought it might be applicable to other fisheries in similar situations. So I'd be happy to talk to any of you about application elsewhere. And with that, I'll thank you for your attention.
Are there any questions? Okay. Oh, did you see one?
Yeah.
Right.
Great talk, and this is sort of a cheating question because I know a lot about the story of snow crab, but my understanding is part of that story as well was the result of the stock being at a record high and thus having so many juveniles in the year of the heat wave. Yeah. Do you feel like there's space in our understanding of kind of future exposure to combine this with an understanding of like the stock status and identify those like collapse vulnerable years in the future before they happen?
Yeah, sorry, I missed part of that maybe because of noise, but you were saying that part of the story is the density of juveniles. Yeah. And can we combine that information into a better understanding of thresholds? Is that right? Yeah. No, thanks. That is a great softball question. And it's true, there's another dynamic at work here, which is that over time, in a more linear fashion, we've seen the footprint of the stock decrease. And we didn't really pay a lot of attention to that, but we were calculating it as part of the management advice for the stock. But it appears that's part of the story, a gradual decrease of the footprint, an increase in density to the highest ever observed levels, then huge spike in metabolic rates perhaps, and density-dependent starvation. So yeah, that's a more elegant way to look at the dynamics.
Thank you.
Okay.
And now we have our next speaker.
Hello, everyone. My name is María Castro, and I'm going to present you here my work that is my master thesis. Now I'm a PhD, but this was my master, and it's about tracking changes in social-ecological system along environmental disturbances with the Ocean Health Index. So as you all know, quantitative estimates of the changing ocean is very important to know how much the ocean is changing, and this is essential for effective management. So we use here Ocean Health Index to check if we were able to track those past changes. So to start with, I would like to present you here our case study that was a small island of Polynesia in the Pacific Ocean. As you may know, the island as this one are very dependent on the ocean and also very vulnerable to climate change, because in light of climate change, the disturbances are each time more intense and also more frequent. And particularly in Moorea, in the past 10 years was the outbreak of a coral predatory starfish from 2007 and 2010 that was very hard on the coral reef, and also a cyclone that was very intense in 2010. So what we do to see those changes was to assess how ocean health and consequently the delivery of ecosystem services change over time. And we use that over the disturbance regime with the Ocean Health Index. And I'm saying ecosystem services because the Ocean Health Index measures ocean health based on how the ocean is delivering these benefits in a sustainable way. So it looks at ocean health with the ecosystem services lenses. You will see later what I mean. So here we have 3 pictures of the coral reef system before the disturbance in 2005, during the disturbance in 2010, and afterwards. And you could see how particularly this area was affected with a decrease in the coral cover in 2010. And what we did was to calculate this index at these 3 different moments of time. So we're like 3 snapshots of the ocean health at that moment. If you don't know, the Ocean Health Index was created by Benjamin Halpern in 2012, which is a professor at the University of Santa Barbara, and it calculates the ocean health based on overall 10 goals or ocean benefits. Here you have an example, like artisanal fishing opportunities, food provision, coastal protection, carbon storage, and livelihoods and economies. So it's not all just about ecology, but it also includes economic information and also, for example, like tourist information. It's very important to apply this index to have a good, range of data over time, because it depends on a lot of data. In our case, was around 50 data layers, of which like the average were local data, and the rest were depending on the Ocean Health database, so the data for French Polynesia. And here, for example, you have some of our main databases that were dependent on the observatory system of Socorail, that it was data from the CRIOP. And here we obtain coral data and also data about temperature, sea level rise, and also sea surface temperature. Then we had also economic data from the Institut de la Statistique de la French Polynesia, sorry. And here we have the economy data, and then, as I said, the Ocean Health Index data. So just to give you a brief understanding about how the index score is calculated. So for the index, we did an average of the different goal score, and then each goal score will depend on current data and on likely future status. So it just not taking into account the present data, but also it will have a calculation estimation of the future data. So in the case of present status, you will need current data available, and you will calculate the status relative to a reference point. And the reference point will depend on each goal, and the reference will be the best condition of our goal. And then you have the likely future status, that both of them will be averaged to calculate the goal score. And the likelihood future status, it will be the present status modified by different dimensions that are resilience, pressure, and trend. So resilience and pressure will depend on the data, like for example, pressure, sea level rise, and also sea surface temperature, ocean acidification. And resilient will be data that have an indication of the resilience of our system, for example, habitat protection, or indices that are more global, like global social progress index, and this we will base on the Ocean Health Index database. So this is just for you to know a bit how this is calculated, and all of this is free, it's available, and you have an R package to calculate this, and you have all functions available in case you want further information. Then going to the results, you have here the OHI, like flower plots at the beginning of, so the before condition. And here you have the different goal scores that I meant before with the different scores. And you will have like from 0 to 100, 100 the blue ones and 0 the red one. And here, just to give you a bit of information, here protected places is 34, so it's like lower, because we use the target of 30% of protection, and it's not meeting this target. Apart from that, in Morea, so far the planning system is still under review, so now the MPAs are changing, and they will have like less MPAs and smaller, so it might be different now. When we compare with the result during the disturbance, you can see that the overall OHI score decreased to 74. And then when you have a look at the different scores, you see that coastal protection and habitats are the ones that decrease the most. So then you see that also these are habitat-related goals. So you will see later what I mean with that. That's overall dependent on the coral condition. Then afterwards, we did also this calculation, and we see that the overall score increased, and then also coastal protection and habitat score like even higher than it was before. So if we get a bit deeper on these calculations, we have here the current status of the different goals. And you see here, maybe a lot of colors, but you see here this one is the coastal protection, and you see that during the disturbance there is a decrease, and then afterwards there is an increase of the coastal protection goal. And then what this may indicate is that the percentage of live coral decreased during the disturbance, which is also in accordance with the reference. And then there is a recovery of the coral system, but of course, this index has its limitations in terms of like the ecosystem functioning. We cannot capture how is the functioning of the ecosystem, but we saw in the literature that there was a recovery depth. So we see here an increase in the coral condition, but there was the functioning of the coral reef was not as good as before those disturbances. So just here to go a bit deeper still, you see here the proportion of live coral, of live hard coral, and you see here the progression, and you see the decrease and then slightly the increase. But it was not as high as like in 2005. And this is dashed line means that 10% of live coral, which is a reference point because it indicates the threshold below which coral reefs have the ability to have a net positive production of carbonate calcium, but above that has this ability, but below it cannot have this positive budget of carbon calcium. So we did also sensitive analysis for the reference point, and we showed that the result was similar for the different reference. So here, I want to go a bit deeper on the different dimensions and to provide you with the limitation that have this ocean health index in terms of capturing the future disturbance. Because as you see here, you have like status and future, what I explained before, and you see that for most of the goals is higher the future status or equal, what has an indication that is the index is overestimating those goal score. And actually, when you go here to here, you see here that the coastal protection is higher, the goal, but the status was lower. But because it's an average between the likelihood future status and the current status, it's giving us a higher score, what also indicates us that there is an overestimation because it cannot capture future disturbance and it was not able to capture this lower future for the future status. And then also it underestimates pressures. We have a lot of data about pressures as pig farming and a lot of farming that is happening in Morea, and some touristic activities such as shark feeding or ray feeding. So there is this limitation about capturing future environmental disturbances. So as this was the session about tracking, measuring these responses of coral system, but also predicting, we can say that OHI is not good at predicting, of course. It was not made for that purpose. But then it can provide an holistic understanding of the changes system. It can capture past disturbance. We saw that it's able to capture those changes over time, but in the past, and also can allow us to see which ocean benefits could be more affected by climate change. Then also can be very useful in terms of management because it's nice to involve managers in the preparation phase to be able to identify which data is missing, which efforts could be prioritized. For example, here, protection needs to be prioritized, and in terms of data collection effort, fisheries should be the priority because we don't have enough fisheries data. It's mostly poorly fisheries data. So this is very important to engage managers, and also there are some studies that are incorporating management effectiveness into the model to see which kind of different type of management, how is the effect on the ocean health. So thank you so much for your attention, and thank you for the conference to provide the opportunity. Thank you so much.
Questions?
Thank you for a great talk. I was curious about your flower plots, and I'm going to ignore the after period because of what you said at the end about your comments at the end, synthesizing the way things perform. But I was really curious that there wasn't a decline in tourism and recreation, and I'm wondering if that surprised you, or is it just an indication that that industry is not dependent so much on the coral reefs being the main attraction for tourists? There were any other surprises in this particular wedges of the flower plot that jumped out to you?
Yeah, regarding the flower plots, I was surprised by the tourists also, because there was no those changes here. And then also, the tourist data comes from the number of jobs that generates the tourist sector. It's not the amount of tourists that comes, but the amount of jobs that are related to the ocean in the island. So, for example, hotel, and also like the restaurants, the activities that generates like in the ocean, like at the boats, like the tourist boats. So it's not about the amount of people that comes into the island. But then, for me, like very surprising also was like the livelihood and economies, because I was expecting to see maybe like the cyclone a change on that, and we didn't. So, but it's also depending on the data and the reference point that you use. Here, the reference is the best performing in the past, so the highest point in the past. So I guess it will depend on your reference points. Thank you.
Thank you. Great. There you go. Oh, you don't need that. Sorry.
Good afternoon, everybody. Thanks for still sticking around. My name is Arani Chandrapavan. I'm from Western Australia. So the west coast of Australia predominantly faces the Indian Ocean, but its ocean conditions are more influenced by what's happening in the Pacific Ocean, largely through the ENSO climate mode. So this is a sea surface temperature anomaly plot for the lower west coast of WA, and you can see these cyclic patterns of cooler than average and warmer than average water temperatures that are largely associated with the El Niño and La Niña phases of ENSO. And La Niña phases of the ENSO are also largely associated with some of the marine heatwave events and periods that this region has experienced. And here are just some examples through some SST map plots. The most well-known event is the 2011 extreme marine heatwave event, which was associated with the record strength La Niña in 2010-11. On the flip side, though, we also experience marine cold spells. So marine cold spells are when the water temperatures are in the lower 10th percentile. And here again are some examples of those. And these are largely associated with El Niños, but not always. Sometimes there are other drivers. And the most intense marine cold spell period we had was actually between 2016 and 2019. And that 2016 SST map there really captures this dichotomy between these two extremes. So we had a marine cold spell on the lower west coast, while we had a marine heat wave on the northwest shelf. The austral summer is also the tropical cyclone season for Australia. And during La Niña years, we tend to have higher number of systems that develop, and also higher number of severe category systems. So in 2010-11, we had about 29 systems that developed, of which around 5 were above category 4. And then more recently, during the 2020 La Niña year, we had this unusual phenomenon occur where we had one system that got absorbed into another system called the Fujiwara effect, which resulted in a much larger intense system that travelled further south down the coast and actually crossed the coastline just north of Perth. So when it comes to understanding some of the impacts of these ocean extremes on our commercial resources, I really want to highlight this through the 3 commercially important invertebrate species that are all challenged by their inability to escape these extremes because of their limited mobility. So we have a blue swimmer crab fishery from Shark Bay, which is a large embayment, shallow, and its movement range is about a few hundreds of kilometres, but contained within that embayment. Then we have a scallop fishery at the Abrolhos Islands, further offshore, just at the edge of the continental shelf, and that occupies deeper sandy bottom habitats about 30 to 40 metres, and its movement range is about tens of kilometres. Then finally, we have an abalone fishery just in the Perth metropolitan area here, and that occupies the subtidal, intertidal platforms, and they don't really move much. They're your true sedentary species. So just listed here are some of the characteristics of these fisheries resources. The common link among all these three species is that they're all broadcast spawners from self-recruiting populations, and so larvae is the most mobile phase of their life history. And it is during this phase that they're most vulnerable to ocean conditions and ocean extremes. So what's important in terms of understanding stock dynamics and that recruitment variability, we do that through stock monitoring and fishery independent surveys. And that really underpins our stock assessments, how we set quotas, how we do catch predictions and stock forecasting. So this first example is the Shark Bay crab fishery. So for this fishery, we do a survey in November at the beginning of the fishing season, and we get an index of recruitment, adult recruitment. That's largely associated with the previous summer temperatures when these crabs are around 6 months old. So these cluster of points largely represent those pre-heat wave years when recruitment was fairly stable, and then we had a significant recruitment decline as a result of that marine heatwave event in 2011. The fishery was closed for a couple of years to allow for that stock to recover. And it did slowly, just as those temperatures cooled down, but really accelerated during that marine cold spell phase, with those cooler than average water temperatures, or summer water temperatures returning back to the region. So you can see in 2019, we had one of the coolest summer temperatures associated with one of the highest recruitment events. Then we went into the latest summers of La Nina, and as expected, those recruitment has slightly declined. The overall biomass has declined, and we're currently in engagement with our stakeholders in terms of reducing the quota for the fishery. Looking ahead though, the summer water temperatures is giving us a catch prediction of what that recruitment should look like when we do our surveys later this year in November. At the moment, it's a big improvement on the last couple of years, so let's see how that turns out. Okay, so next is the Perth abalone fishery. So again, we have quite a good catch prediction model here that's based on the stock recruitment environment relationship. So on the y-axis here, on the y-axis here, we have an index of juvenile abundance, x-axis, sorry, and the y-axis here, we got an index of adult abundance 4 years later, because this is a long-lived species. And that's associated with the summer temperatures, average summer temperatures in the intervening 4 years. So these years, pre-heat wave years along that green regression line are fairly stable. Summer temperatures were not that variable. Then we had the 2011 marine heatwave event. During the heatwave event, we had high mortality of all size classes of abalone, so the overall biomass had declined, spawning biomass had declined, and so recruitment in the following years slowly declined as well. However, just as we entered that marine cold spell phase and water temperatures were much cooler than average, the remaining animals actually exhibited faster growth rate. And so from 2019 onwards, we've got biomass that's actually higher than our pre-heat wave years here. Looking ahead, the prediction for 23 and 24 is currently based on those surveys of recruitment indices that we already have, that we've done previously, and on the summer temperature data that we currently have. So at the moment, it's telling us that be prepared for lower biomass because we had a marine heat wave event, a moderate one in 22. So 23 and 24 prediction at the moment is looking quite poor, back to those marine heat wave years, and that's likely to result in lowering of the quotas in the coming seasons. So next, I'm just going to show you a video from our stakeholder point of view to introduce.
There's no climate change deniers in the scallop fishery. We've lived and experienced it already. My name's Hamish Chung. I'm the Managing Director of Far West Scallops. Our family's been involved in the roller scallop fishery since the mid-1980s. We have our own fleet of vessels, a processing factory just outside of Fremantle. We employ approximately 70 people. I think in the roller scallop fishery we've already seen the impacts of climate change. We had a marine heat wave in 2010, 2011, which just fundamentally just wiped out the stocks, and the fishery took 5 years to recover. With hindsight, you can see exactly how it panned out, but at the time, in the season that the heat wave actually occurred, we had one of the best seasons we'd ever had. The water temperature was certainly there, we certainly noticed that, but it didn't seem to have any impact on the stock. But come the surveys, 6 months after the season had ended, the stocks had literally disappeared, and they disappeared for 5 years. And seasons come and go, you have good seasons, you have bad seasons, but we really hadn't experienced no seasons. What we did find out is that recovery of the fishery requires time and monitoring and literally no fishing effort. The impacts of the heat wave to our business were catastrophic, and it's not just as simple as no fishing, no income. You still have to retain, your fishing assets.
So similar to the sharkbait crab and the abalone fishery, we've got pre-heat wave recruitment indices here, and that represents your good seasons and your bad seasons. Then we have a decline in 2011, the heat wave event, then a recruitment failure, stock collapse in the following years, and then recovery starting to occur around 2015, and then kind of fully recover because of those cooler temperatures from that marine cold spell. Now, 2019, at the end of 2019, is when the Australian Bureau of Meteorology puts out our ENSO forecast, and it said that you're going to go into a La Nina. Now, at that point, we hadn't seen a La Nina return to this region for almost a decade. So we're really curious to know how the stock was going to respond to these warmer summer temperatures again. We did the survey in November 20, and as expected, recruitment had declined in response to those warmer temperatures, and the catches in the following year was, average to below average. Then during 2020, the Bureau puts out the forecast again, saying you're likely to go into a double dip La Nina, and then you're like, okay, great, let's see how that's going to pan out. And we did the survey in 21, and recruitment had declined much lower than what we had expected, and to a level that we had to close the fishery, as according to the harvest strategy of this resource. Then during 21, again, the Bureau puts out the forecast, and it's not good news. It says we're now having a really rare triple dip La Nina that's coming along. We did the survey, we consulted with our stakeholders, we told them don't expect, probably not to expect another fishing season. And lo and behold, we were completely surprised by our survey results. We had really good recruitment that actually survived over those summer months. And here is a kind of an example of where there's been a mismatch between the predictor stock response with that forecasted information that we were relying on. And that kind of really highlights the fact that we need to use a suite of information. So I've been using sea surface temperature data, but what we really need is more of those in situ measurements as well to inform some of these models and relationships. Sorry, I'm running out of time. So the prediction for 23 is looking better, and hopefully that doesn't lead to another mismatch of information. So just to bring it all together again, from a regulatory perspective, broad-scale climate forecast information such as ENSO kind of really acts as a warning system for us. And using that information, we can then take some actions in terms of increasing our monitoring, redirecting our resources to those fisheries that really require them more than others. But most importantly, we're using that information to communicate it with our stakeholders to kind of manage their expectations of what those future seasons are likely to be. What they do with that information is part of a much more complex space, which we don't have time to go into today. So our current research activities and directions are really focused on more real-time monitoring of our nearshore habitats, much more subsurface, in situ measurements, and also downscale regional seasonal forecast information, which really captures these small areas that are more relevant to the fisheries that we are managing with all these research partners in Western Australia. Thank you. Sorry.
Questions?
That was a really great talk. Thanks, Arani. I was wondering if you had any thoughts inspired by some of the talks we've seen today that temperature isn't explaining everything. Not every marine heat wave has the exact same impacts. And so are there any variables or any other ways that you could kind of consider other ecosystem components like primary productivity that we've seen is a big one?
Yeah, I think that's my biggest takeaway from this conference, is that using just a single predictive variable is not the way to go about it. You have to look at it more holistically. There are Shark Bay, for example, is a much more complex system, and definitely the most ecosystem approach and understanding productivity proxies or variables. It's the biggest barrier to that is one, expertise, in-house expertise, resources. We work with very limited resources, and so trying to utilise freely available information is kind of the direction we're going in. But for the future, definitely looking at engaging with the wider research community to kind of bridge those knowledge gaps, I guess, yeah.
Great. Thank you. And last but not least is our co-convener, Stephanie Brown.
Okay, hi everyone. Thanks for sticking around. I'm glad we're at the end of this session. I've been incredibly inspired so far. What I'm going to be talking about is ecological forecasts for resource management during climate extremes, and it does link back to a few talks that we've had today, so hopefully it's still interesting. Okay, so we've heard all week that society is increasingly facing novel and uncertain environmental conditions. These changes are really cascading down to the ecosystem level and causing unprecedented impacts, from species redistributions to negative wildlife interactions, bycatch entanglement, and through all the way to just our general ocean health. And so these kind of climate extremes are really posing a huge challenge for marine management. We've had a lot of talks on that today. And to really understand and prepare for these changes, we need accurate predictions, and we need them across all forecast horizons. It's much easier said than done. When we think about forecasting, then we really need to consider that decisions do change across timescales. So in the kind of nowcast and short term, we might think about how weather is impacting fishing. As we kind of move forward in time at seasonal timescales, decisions might be based on when to harvest or hire labour. And then as we move further in time, and we touched on this in the discussion today, these annual, multi-annual and long-term timescales, it's more about thinking about strategic decisions and resilience. So there's a really strong argument that forecasts at these intermediate timescales are actually most important to resource management, who are faced right now with uncertainty and climate extremes, and they need to kind of understand what's going to happen in the near term for their fishery or their resource that they're managing. And so given the need that we need to rapidly adapt to climate change, we really need to kind of build on existing tools that we have and see if we can actually assess their ability to actually transition to a forecasting format rather than a kind of nowcasting or historical format. And so this is some work that Mike Jacox presented on earlier, where he actually ranked the feasibility of some existing management tools and how likely they are to succeed as a skillful forecast. And so from this ranking, we pulled out two examples, and two case studies I'll step through today, which is loggerhead bycatch in a swordfish fishery off the California coast, and whale entanglement in a crab fishery, which Bill just very nicely detailed in his talk. So for these two existing management tools, we force our forecasts using global sea surface temperature forecasts output from the North American Multi-Model Ensemble, the NMME, They are 6 global forecast models, and they each kind of produce up to 73 different ensemble members, and these are produced in an operational capacity. So in our first case study, this is kind of looking at crabs, whales, and climate change. This is the same fishery and the same whales that Bill was just talking about. So we have this situation when we have environmental variability. I've put marine heat waves here as an example, but it's not just marine heat waves. They drive overlap between whales and the crab fishery. That leads to spikes in entanglements and ultimately fishery closures. And these closures are very effective at saving whales, but they come at a very large economic cost to the fishery. So Bill mentioned and introduced the Habitat Compression Index, and this is an index that was built by Jared Centaur to help management understand when there might be these high entanglement risk events. And so this is this idea that whales forage in nutrient-rich upwelled water. So if you can understand how much upwelled water there is, then you might have an understanding of how many whales will be foraging in there. And so the index is basically calculated off the area of upwelled water. Here is an example in 2013 of just the sea surface temperature in the area, with the blue showing upwelled water. In 2016, when the marine heat wave hit, you can see that this upwelled water is very narrow and really compressed along the coast. And this is why we have this habitat compression, or why the index is called habitat compression. And when you have high compression, like in 2016, you get high entanglements. So this area of upwelled water decomposes really nicely into a time series. This is a time series from 81 to 2020, and everything shaded in red are the values below the mean, and that's what we consider high compression. And so because this is effectively a modified sea surface temperature index, we can use forecast sea surface temperature instead of observed sea surface temperature, and try and push out our lead time for when we might expect high compression events. And so this is an example forecast of habitat compression, and I've just zoomed in on the marine heat wave period from 2014 to 2017, here shaded in grey. And so what we have here is the observed habitat compression in black, and you can see it's kind of bopping around the mean, and then it dips below this black line. We have high habitat compression throughout the entire marine heat wave period. The coloured lines represent our forecasts for that exact same period, 1 month, 6 months, and 12 months in advance of that marine heat wave. And you can see that all these coloured lines dip below their corresponding kind of horizontal thresholds for what we consider compression. And so in this example, if kind of in a retrospective sense, we could have predicted these high habitat compression events 1 month in advance, which could have given management a little bit, and the fishery a little bit more lead time to understanding the threat and risk of entanglements for that season. So we can kind of calculate those forecasts for every month and year historically, and assess how well we did. So here we have the correlation between the observed and forecast habitat compression for each month of the year along the x-axis, and for each lead time, so going from 1 to 12 months into the future. And this is just the correlation between the two, with black dots indicating significance. And so you can see around about 4 months into the future, at every month of the year, we had really good skill, significant skill in being able to predict those high compression events. And most importantly, during spring, which is kind of when management really wants to know if high compression is going to happen, we actually have a lead time, skillful lead time out to 1 year in advance. Okay, so I will jump into the second case study, which is very similar, loggerheads in hot water. And so off the US West Coast, when we have marine heat waves or El Niño or warm water events, we have loggerheads that extend their distribution up along the coast into the Southern California Bight, which overlaps with the swordfish drift gillnet fishery. in advance of, when those warm water events occur, there is a seasonal fisheries closure that's implemented to reduce and stop bycatch events. And so in this kind of square area in the California Bight, our index for whether a fishery should close, the fishery should close or not, is basically the 6-month sea surface temperature anomalies. And when they exceed this threshold here, shown by the red line, there is a recommended closure to reduce bycatch. And so, because again we have a lovely time series of sea surface temperature anomalies, we can use forecast sea surface temperature instead of observed to try and increase that lead time for management. And so what this looks like is here, a time series. Again, the black line is the observed closure risk, or the sea surface temperature anomalies. When it exceeds this horizontal threshold, a closure is recommended. And our coloured lines represent the lead times for those forecasts, 7, 9, and 12 months into the future. And again, you can see that all of these forecasts are correctly predicting those sea surface temperature anomalies in advance. And in fact, when we actually look at the retrospective skill assessment from 1981 to 2020, every single closure month, at every single lead time, we had significant skill. So we have a lot of ability to kind of really predict these warm water events in this region. Okay, so we were really encouraged by these results. This is kind of demonstrating that ecological forecasts are skillful and feasible in this region. And so we wanted to go one step further and examine the role of downscaled seasonal forecasts for this area. And so this is some work that Mike presented earlier in the session, if you were able to catch it. What I've presented so far is these kind of global SST forecasts. They're 1 degree resolution, they're initialized once per month. And there's 73 different ensemble members that we can access. But if we move to the downscaling approach, or dynamically downscale these forecasts, you can see exactly how much more that's spatially resolved, and you can get daily forecasts at that level. But doing this downscaling is incredibly expensive. And so we only looked at 3 ensemble members. We only downscaled 3 ensemble members. And we wanted to kind of examine exactly what the trade-offs were. You know, is it better to work at a much finer spatial resolution with only a handful of models, or is it better to stay coarse and use all 73 ensemble members? And spoiler alert, no, you don't. There's better skill actually in using a greater number of ensembles, but I will step through it. So here in the middle, we have those correlation values I presented earlier for the habitat compression index. So each point here is each of those forecasts at each lead time for each 12 forecast months. And I've just put it into a box plot instead. And so you can see here what the general kind of spread of correlation skill is when we use all 73 ensemble members at the global resolution. If we only select those 3 ensemble members but keep it at that core scale, we have a dramatic drop in skill. And then if we downscale those 3 ensemble members, our skill goes back up, but it doesn't go up high enough to beat those kind of global 73 ensemble members. So in an absolutely perfect world, if we had unlimited money and power, we would downscale all 73 ensemble members. We also do other things, but for that you would downscale all 73. But that's not feasible. So there's this really interesting kind of trade-off between, depending on your purpose and how you want to forecast, you don't have to wait for regional downscaling to occur. There are global SST forecasts readily available in an operational format that can be used. So we were really inspired by this. We developed a guide for practitioners who are kind of faced with this problem. And I think I'm almost out of time, so I'm not going to step through all the details of this, but it really just kind of has some considerations for practitioners. But I think most importantly, and what I'm most excited about, is that I think this really increases capacity for more people to use global forecasts. You don't have to wait for regional downscaling to occur. You don't have to be an expert in how to dynamically downscale. I certainly am not. And so I think there's really some potential for ecological forecasting to be
used more around the world by using these kind of tools that are already existing. So in summary, I showcase capacity for management tools, existing management tools, to transition to a forecasting format. We don't need to reinvent the wheel. We can just use what we already have, but try and increase the lead time for management. Forecasts can forewarn human-wildlife interactions. These I showed 2 case studies in the California current. And the final kind of summary is don't wait for regional downscaling unless you have unlimited money and power. And with that, I'll thank all my co-authors for this work. Thanks.
Questions for Steph?
Hi, Benjamin Plong from IMR in Tromsø. Thanks for the very interesting talk. I have a comment more than a question, and it's on the use of correlation as a measure of skill.
Yes.
Because it can be very misleading, especially on time series. And maybe, so the risk is that you have an apparent skill that is much higher than your true skill. But maybe one key thing is to adjust the skill to the management issue that you are trying to deal with, and measure how many times would you have given the right advice to your management body, having the forecast and not having the forecast. And that's maybe a much better measurement of your true forecasting skill, because it really measures the skill of the forecast for the purpose of the forecast.
Yes, yeah, exactly. And I have done that. I just didn't show the results, but I have calculated forecast accuracy and SETI, which does exactly that. It kind of converts it to, did we actually forecast an event? Did that event happen? And kind of vice versa. And the results are consistent with that. I just thought in the time I had, correlation was a little bit easier to kind of convey. But the results are, show the exact same trends. But great point. In future, I'll make sure I show all 3 indices.
One last question.
Hi, thanks for the talk, really good. Do you think that this would be the same result for other parts of the world? Because we know that these global models simulate really well that region of the west coast of the US, but not probably the South Atlantic, for instance. And then in that case, the downscale would be maybe have better results. Do you have any thought about this? Do you have an idea if it is region dependent?
Yeah, I think it will be region dependent, and it really will also depend on the region, but okay, that was very circular. So one example, I'll just list an example. I know I was talking to a researcher based in the UK who was interested in using forecasts, and if they didn't have a downscaled model, they weren't able to capture a certain current, and that current in the global model would go poleward, but in reality it goes southward, and when they downscale it, it goes in the correct direction. But if you use those global forecasts, then you would be doing the completely wrong thing. So there would be definitely some regional dependencies there. And it's also going to depend on the variable you're interested in too. Like if you want some biogeochemical variables, then you're probably going to have to downscale. But yeah, as always, there's kind of trade-offs in how much power you can have. But you know, my talk and Mike's talk did show that if you do downscale, you can get really good skill and improve that above what the global forecasts have.
Thank you.
Thanks.
And thank everyone for coming to this session.